Let's start with something that shouldn't exist. At least, not according to what we thought we knew about how the universe works. In 2013, a team of astronomers led by Istvan Balatz and his colleagues were doing something that might sound mundane on the surface. They were mapping gamma-ray bursts. These are the most violent explosions in the universe, the dying screams of massive stars collapsing into black holes. Events so energetic that for a few seconds they can outshine entire galaxies. We'll talk more about gamma-ray bursts in a moment, but what matters here is that these astronomers were plotting where these bursts appeared in the sky and how far away they were. And they noticed something strange. The gamma-ray bursts weren't distributed randomly across the universe, as you might expect. Instead, they found a clustering, a massive clustering. The bursts were arranged in a pattern that suggested an underlying structure, something connecting them, something holding them in place across unimaginable distances. When they mapped this structure, when they calculated its dimensions, they found something that made them question their own data. They found a galactic filament stretching approximately 10 billion light-years across space. 10 billion light-years. Let that number sit with you for a moment. We're not talking about something the size of a galaxy. We're not even talking about something the size of a galaxy cluster or a supercluster. We're talking about a structure so large that it spans roughly 1/10 of the entire observable universe. A structure so vast that calling it large feels almost meaningless because we have no frame of reference for comprehending what that size actually means. They named it the Hercules Corona Borealis Great Wall, after the constellations where it appears in our sky. The name is fitting because in mythology, Hercules was known for accomplishing impossible tasks, and in many ways, the existence of this structure seemed impossible. Here's what the Hercules Corona Borealis Great Wall actually is. It's a galactic filament, which means it's not a solid object. You couldn't stand on it or touch it. It's more like a highway of galaxies, a cosmic thread along which thousands of galaxies are strung like beads on an impossibly long necklace. These galaxies are connected by gravity and by the invisible scaffolding of dark matter that we'll discuss later. They're not randomly scattered. They're organized, arranged, following a pattern that emerged from the conditions of the early universe. The discovery challenged fundamental assumptions about how the universe is structured. You see, cosmologists have long worked under something called the cosmological principle, which states that when you zoom out far enough, the universe should look uniform in all directions. There shouldn't be any structure beyond a certain scale. Everything should average out to smoothness, like looking at a smooth beach from far away, even though up close you can see individual grains of sand. But the Hercules Corona Borealis Great Wall suggested that the universe has structure at scales far larger than this principle would allow. It's as if you stepped back from that beach, and instead of seeing smoothness, you saw massive organized patterns stretching across the landscape. The discovery was controversial from the start. Some astronomers questioned whether this was really a single coherent structure, or whether it was several separate structures that just happened to align along our line of sight, creating an illusion of connection. Others suggested that the clustering of gamma-ray bursts might be a statistical fluke, a random pattern that our pattern-seeking brains interpreted as meaningful, when it was actually just cosmic coincidence. These debates continue today. The Hercules Corona Borealis Great Wall has not achieved the same level of confirmed status as some other large structures we've found. But whether it's truly a single connected filament or a chance alignment, its discovery forced astronomers to think more carefully about the maximum size that cosmic structures can achieve, and about what we mean when we say the universe is homogeneous at large scales. What made this discovery particularly significant was the method used to find it. Previous large structures had been discovered by mapping galaxies directly, by pointing telescopes at the sky, and cataloging where galaxies appear. But the Hercules Corona Borealis Great Wall was found through gamma-ray bursts, which are much rarer events, but also much brighter, and therefore visible across much greater distances. This opened up a new way of mapping the universe. If gamma-ray bursts trace the distribution of galaxies and stars across cosmic time, then by mapping these bursts, we can see structure that would be invisible through other methods. We can peer deeper into space and further back in time, revealing the architecture of the universe at scales we couldn't observe before. The structure itself is located about 10 billion light-years away from Earth. This means the light we're seeing from it left when the universe was only about 3.8 billion years old, less than a third of its current age. We're not seeing this structure as it is today. We're seeing it as it was in the ancient past, when the universe was young, when our own solar system hadn't formed yet, when the Milky Way galaxy was still assembling itself from smaller pieces. Think about what this means. The Hercules Corona Borealis Great Wall existed when the universe was young. It had already assembled itself into this massive structure within just a few billion years after the Big Bang. This is challenging because structure formation takes time. Gravity works slowly, pulling matter together bit by bit. The fact that something this large could form so early in cosmic history suggests that either our models of structure formation are incomplete, or that the initial conditions in the early universe were different than we assumed. What does this structure actually contain? It contains thousands of galaxies, each one a collection of hundreds of billions of stars. It contains vast clouds of gas and dust stretching between those galaxies. It contains dark matter, the invisible substance that makes up most of the mass in the universe, forming the gravitational framework on which everything else hangs. And it contains uncountable numbers of planets, most of which we'll never see, orbiting stars we'll never observe, in galaxies whose light is so faint and distant that it pushes the limits of our most powerful telescopes. The total mass of the Hercules Corona Borealis Great Wall is difficult to calculate precisely, but estimates suggest it contains the equivalent of trillions upon trillions of stars like our Sun. The number is so large that it ceases to have meaning in human terms. You could spend your entire life counting and not make a dent in that number. And yet, despite its enormous size, the Hercules Corona Borealis Great Wall is mostly empty space. Like everything in the universe, it's sparse. The galaxies within it are separated by millions of light-years of near vacuum. If you were somehow placed randomly within this structure, the overwhelming likelihood is that you'd find yourself in darkness, surrounded by nothing, with the nearest galaxy so far away that it would appear as barely a faint smudge against the cosmic microwave background. This is the nature of the universe at the largest scales. It's a universe of vast emptiness, punctuated by tiny islands of matter. And even those islands are mostly empty when you look closely. Stars are separated by light-years within galaxies. Planets are separated by millions of miles within solar systems. Atoms are mostly empty space within matter. Emptiness all the way down and all the way up. The discovery of the Hercules Corona Borealis Great Wall marked a turning point in our understanding of cosmic structure. It showed us that the universe is capable of organizing itself at scales larger than we imagined. It raised questions about the limits of structure formation, about how gravity and dark matter work across billions of light-years, about whether our models of cosmology are complete, or whether there's something we're missing. But perhaps most importantly, it reminded us that the universe is still capable of surprising us. Even after centuries of astronomical observation, even after decades of sophisticated computer simulations, even after mapping billions of galaxies and measuring the cosmic microwave background to exquisite precision, the universe can still show us something new, something that makes us step back and reconsider what we thought we knew. The Hercules Corona Borealis Great Wall is a monument to the scale of the cosmos. It's a reminder that we live in a universe far larger and far stranger than our ancestors ever imagined. And it's a challenge to our understanding, pushing us to refine our theories, to question our assumptions, to keep looking up and asking what else might be out there waiting to be discovered. Now we need to talk about what it actually means when we say something is 10 billion light-years across, because that number, as I said it, probably didn't register as anything more than abstract symbols in your mind. And that's completely understandable. Our brains didn't evolve to comprehend distances like this. Let's build up to it slowly, starting with something more manageable. A light year, despite having the word year in it, is not a measure of time. It's a measure of distance. It's the distance that light travels in 1 year. And light is fast, unimaginably fast by any standard we experience in daily life. Light travels at about 186,282 miles every single second. Every second, not every hour or every day. Every single second, light covers a distance greater than the distance around Earth's equator 7 times over. When you flip a light switch in your house, the light reaches your eyes essentially instantaneously because the distance is so short. The room is maybe 20 feet across. Light covers that distance in about 20 nanoseconds, 20 billionths of a second. Your brain can't even register the delay. But let's scale up. The moon is about 238,855 miles from Earth. When you look at the moon in the night sky, you're seeing light that left the moon's surface about 1.3 seconds ago. The moon you see is the moon as it was 1.3 seconds in the past. This delay is small enough that it doesn't matter for any practical purpose, but it's real and measurable. Our sun is about 93 million miles from Earth. When you look at the sun, and please don't look directly at the sun, you're seeing light that left the sun's surface about 8 minutes and 20 seconds ago. If the sun were to suddenly vanish, which it won't, but if it did, we wouldn't know for 8 minutes and 20 seconds. We'd keep seeing it, keep feeling its warmth, keep orbiting the spot where it used to be, until the information about its disappearance had time to reach us traveling at the speed of light. This 8-minute 20-second distance is called an astronomical unit, and it's one of the standard measurements in astronomy. It's a useful scale for measuring distances within our solar system. Neptune, the outermost major planet, is about 30 astronomical units from the Sun, meaning light takes about 4 hours to travel from the Sun to Neptune. But when we start talking about distances to other stars, astronomical units become cumbersome. The numbers get too large. This is where the light year becomes useful. Light travels 186,282 miles per second. There are 60 seconds in a minute, so in 1 minute, light travels about 11.2 million miles. There are 60 minutes in an hour, so in 1 hour, light travels about 671 million miles. There are 24 hours in a day, so in 1 day, light travels about 16 billion miles. And there are 365 days in a year. Multiply all of these together, and you get approximately 5.88 trillion miles. That's 1 light year. The distance light travels in 1 year of continuous motion at 186,282 miles per second. 5.88 trillion miles is already a number that's hard to comprehend. If you tried to drive that distance at highway speeds, 65 miles per hour, never stopping, never slowing down, it would take you about 10.3 million years. Civilization has existed for perhaps 10,000 years. You'd need more than 1,000 iterations of all of human civilization just to complete that 1 light-year drive. The nearest star to our solar system, other than our Sun, is Proxima Centauri. It's about 4.24 light-years away. The light you see from Proxima Centauri tonight left that star over 4 years ago. It's been traveling through the darkness of space for more than 4 years, covering nearly 25 trillion miles to reach your eye tonight. If you wanted to send a message to someone on a planet orbiting Proxima Centauri, assuming such a person exists, your message traveling at the speed of light would take 4.24 years to arrive. Their response would take another 4.24 years to return. A simple back-and-forth exchange would span 8.48 years. You could ask someone a question when you're 20 years old and receive their answer when you're 28, assuming they responded immediately. The Milky Way galaxy, our home galaxy, is roughly 100,000 light-years across. If you were positioned on one edge of the galaxy and tried to send a message to someone on the opposite edge, that message would take 100,000 years to arrive. When the light we see from the far side of the Milky Way began its journey toward us, humans didn't exist yet. Neanderthals didn't exist yet. Homo erectus was still walking the Earth. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.537 million light-years away. When you look at Andromeda in the night sky, and you can see it with your naked eye if you know where to look, and the sky is dark enough, you're seeing light that left that galaxy 2.537 million years ago. When that light began its journey toward Earth, our earliest human ancestors were just beginning to diverge from other primates. Stone tools were being invented. Everything we recognize as human civilization has happened while that light was traveling through space toward us. Now, with that foundation, let's talk about 10 billion light-years. 10 billion light-years is 10 billion light-years. Each light-year is 5.88 trillion miles. Multiply these together, and you get about 58.8 sextillion miles. That's 58 sextillion, 800, and quintillion miles. If you tried to count to that number, counting one number per second without ever stopping, it would take you about 1.86 quintillion years. The universe is only 13.8 billion years old. You'd need about 135 million universes worth of time to finish counting. If you tried to drive that distance at highway speeds, it would take you about 103 quintillion years. Stars would be born, live their entire lives, and die as you drove. Galaxies would collide and merge. The universe would expand dramatically, and you still wouldn't be halfway there. Let me give you another comparison. The observable universe, the entire sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall, at 10 billion light-years across, spans approximately 1/10 of the observable universe. Imagine standing in the center of a sphere 93 feet in diameter. You're at the center, able to see 46.5 feet in any direction. Now imagine a structure within that sphere that's 10 feet long. That's the proportion we're talking about. The Hercules Corona Borealis Great Wall is to the observable universe what a 10-foot object is to a 93-foot sphere. Except we're not talking about feet. We're talking about distances so vast that light, traveling at 186,282 miles per second, takes billions of years to cross them. When we observe the Hercules Corona Borealis Great Wall, we're seeing different parts of it at different times in cosmic history because of how long light takes to travel. The near edge of the structure might be 9.5 billion light-years away. The far edge might be 10.5 billion light-years away. That's a difference of a billion light-years. A billion years of cosmic time during which the universe was evolving, stars were forming and dying, galaxies were colliding and merging. We're not seeing the structure as a snapshot frozen in time. We're seeing it smeared across a billion years of history, each part showing us what it looked like at a different epoch. Think about what was happening in that structure 10 billion years ago when the light we're now seeing left. The universe was only about 3.8 billion years old. Our sun didn't exist. Our solar system didn't exist. Earth didn't exist. The Milky Way was still forming, still gathering mass, still colliding with smaller galaxies and absorbing them. Life hadn't appeared anywhere in our corner of the universe. And yet, 10 billion light-years away, this massive structure already existed. Thousands of galaxies were already arranged along this cosmic filament. Stars were forming, living, dying. Planets were being born. Perhaps, somewhere in one of those galaxies, life was emerging, looking up at their own sky, wondering what else was out there. The light from those events has been traveling toward us ever since. While that light was in transit, the universe aged by 10 billion years. Our sun formed. Earth coalesced from a disk of debris. Oceans filled. Life appeared. Evolution produced the entire tree of life we see today, from bacteria to plants to animals to humans. Civilization arose. We invented writing, mathematics, the telescope, and finally, the ability to detect and map gamma-ray bursts. And only now, 10 billion years after that light began its journey, does it arrive at our telescopes, carrying information about a structure so large that it challenges our understanding of how the universe works. This is what we mean when we say the Hercules Corona Borealis Great Wall is 10 billion light-years across. We mean that light takes 10 billion years to travel from one end to the other. We mean that the structure spans 1/10 of all the space from which light has had time to reach us since the beginning of the universe. We mean that it contains a significant fraction of the matter within our cosmic horizon. The human mind isn't built to grasp these scales intuitively. You can't visualize 10 billion light-years the way you can visualize 10 feet, or even 10 miles. The numbers are too large, they exceed our cognitive capacity. But we can understand them mathematically. We can work with them, calculate with them, use them to describe reality. And through that mathematical understanding, we can begin to appreciate the sheer magnitude of the universe we live in. You exist on a planet 7,917 miles in diameter, orbiting a star in a galaxy 100,000 light-years across, which is part of a universe containing structures 10 billion light-years in extent. The ratio between your size and the largest structures in the universe is beyond any number that has meaning in everyday human experience. And yet here you are, aware of these structures, learning about them, incorporating them into your understanding of reality. That's remarkable when you stop to think about it. Now that we've established the scale of what we're talking about, we need to understand what these structures actually are. What is a galactic filament? What does it mean to say that galaxies are connected across billions of light-years? Let's start with a simpler question. Where are galaxies? If you were to plot the positions of all the galaxies in a large volume of space, creating a three-dimensional map, you might expect to see them distributed randomly, scattered like grains of sand thrown into the air. After all, space is vast, and galaxies are small by comparison. Why would they show any pattern? But when astronomers actually did this, when they mapped hundreds of thousands of galaxies and plotted their positions, they found something completely unexpected. The galaxies weren't scattered randomly at all. They were organized. They formed patterns, structures, architecture. Galaxies cluster together in groups and larger clusters. Multiple clusters align along elongated structures called filaments. And between these filaments lie vast empty regions called voids, where almost nothing exists. This is the cosmic web, and it's one of the most striking features of the universe at the largest scales. Galactic filaments are the threads of this cosmic web. Think of them as highways made of galaxies, long narrow structures along which matter flows, stretching across hundreds of millions or even billions of light-years. Along these highways you find galaxy clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. And connecting those clusters are thinner sections, bridges of galaxies and gas and dark matter, linking the nodes of the web. The filaments aren't solid. You couldn't walk on them. They're more like preferred paths along which matter has accumulated over billions of years. Imagine water flowing down a landscape, following the paths of least resistance, carving out valleys and streams. Galactic filaments are similar, except instead of water flowing downhill under Earth's gravity, it's matter flowing through space under the influence of cosmic gravity fields created primarily by dark matter. The width of a typical filament might be tens of millions of light-years. The length might be hundreds of millions or even billions of light-years. Within that volume, The density of galaxies is higher than in the surrounding space, but it's still not what you'd call crowded. A typical filament might contain a few galaxies per cubic megaparsec. A megaparsec is about 3.26 million light-years, so we're talking about vast volumes of space with only a handful of galaxies in them. And yet, compared to the voids between filaments, this is dense. The voids are almost completely empty, containing perhaps 1/10 or 1/20th the average density of the universe. This creates a structure that resembles a sponge or a bath sponge, if you can imagine it in 3 dimensions. Dense filaments forming a network around empty voids, or like a neural network, with nodes connected by threads, information flowing along the pathways. The cosmic web emerged naturally from the initial conditions of the universe. Shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density, perhaps 1 part in 100,000. Some regions were very slightly denser than others, and those tiny variations were enough. Gravity works by pulling matter toward matter. Dense regions attract matter from their surroundings, becoming denser still. Less dense regions lose matter to their neighbors, becoming emptier. Over billions of years, this process amplifies small differences into large ones. The slightly denser regions became the filaments and clusters we see today. The slightly less dense regions became the voids. And the structure grew more pronounced over time as gravity continued to pull matter from voids into filaments and from filaments into clusters. But the process isn't random. The pattern of density variations in the early universe had structure built into it, imprinted during the first fraction of a second after the Big Bang by a process called cosmic inflation. This structure created preferred scales, characteristic distances at which density variations were stronger. These preferred scales show up in the cosmic web. Filaments have typical lengths. Voids have typical sizes. Clusters have typical separations. The universe isn't completely random. It has patterns, regularities that emerged from the physics of the early universe. Galactic filaments contain more than just galaxies. They contain vast quantities of gas, mostly hydrogen and helium, the primordial elements left over from the Big Bang. This gas fills the space between galaxies within the filament, too diffuse to form stars, but dense enough to be detected through its absorption of light from more distant sources. They also contain dark matter, the mysterious substance that makes up about 85% of all matter in the universe. Dark matter doesn't interact with light, so we can't see it directly, but we can infer its presence through its gravitational effects. And those effects are enormous. Dark matter forms the underlying scaffolding of the cosmic web. It's the dark matter that creates the gravitational potential wells along which ordinary matter flows. The galaxies we see are like foam on the surface of an ocean of dark matter, visible markers of an invisible structure. If you could somehow see dark matter, the filaments would look much thicker, much more substantial. You'd see enormous threads of dark matter stretching across the universe, with galaxies embedded within them like jewels in a necklace. The matter in filaments is in motion. Galaxies aren't static. They're falling along the filament toward the nearest massive cluster, accelerating under gravity. At the same time, the expansion of the universe is stretching the filament, trying to pull everything apart. These two effects, gravity pulling inward and expansion pushing outward, are in competition. In the densest regions, gravity wins and structure continues to grow. In the less dense regions, expansion wins and structure stops growing or even begins to dissolve. This creates a dynamic, evolving web that changes over cosmic time. In the early universe, filaments were shorter and thicker. Voids were smaller. The contrast between dense and empty regions was less extreme. Over time, as structure continued to grow, filaments stretched and thinned. Voids expanded. The web became more pronounced, more spidery, more delicate. And this process is still ongoing. The cosmic web you'd see if you could map the universe today is different from the cosmic web that existed a billion years ago, or that will exist a billion years in the future. It's evolving, changing, responding to the competing influences of gravity and cosmic expansion. The Hercules Corona Borealis Great Wall is an extreme example of a galactic filament, one of the longest ever detected. But it's not fundamentally different from other filaments. It's made of the same components: galaxies, gas, dark matter. It formed through the same processes, gravity amplifying primordial density variations. It's just bigger than most, pushing against the theoretical limits of how large these structures can grow. Understanding galactic filaments is essential to understanding the large-scale structure of the universe. These aren't just interesting patterns. They're the result of fundamental physical processes operating over cosmic time. They encode information about the initial conditions of the universe, about the nature of dark matter and dark energy, about how gravity works across billions of light years. When we map the cosmic web, when we trace the filaments and measure their properties, we're doing cosmology. We're testing our theories of how the universe began and how it evolved. We're looking for deviations from our models, anomalies that might point to new physics, and structures like the Hercules Corona Borealis Great Wall are particularly valuable because they're so extreme. They push our models to their limits. If our theories can explain why this structure exists, how it formed, what its properties should be, then we gain confidence that we understand the universe correctly. If they can't, then we know there's something missing, something we need to figure out. The cosmic web is architecture on the grandest scale imaginable. It's the skeleton of the universe, the framework on which all smaller structures hang. Understanding its architecture means understanding how the universe is organized at the largest scales. Let's zoom out. Imagine you're looking at the entire observable universe from the outside, which is impossible but useful for visualization. What would you see? You'd see a foamy, spongy structure, dense regions forming interconnected networks around vast empty bubbles, filaments stretching between nodes, sheets of galaxies forming walls around voids, and embedded throughout, the dark matter scaffolding that holds it all together. The cosmic web has four main components: nodes, filaments, sheets, and voids. Nodes are where filaments intersect. These are the galaxy clusters, the densest concentrations of matter in the universe. A typical node might contain hundreds or thousands of galaxies bound together by gravity, embedded in halos of dark matter hundreds of millions of light years across, surrounded by hot gas heated to millions of degrees by the gravitational compression. At a node, matter has accumulated over billions of years, flowing along the filaments and settling into a dense concentration. Gravity is strongest here, and the effects are dramatic. Galaxies move at high speeds, sometimes colliding and merging. The hot gas glows in X-rays. The dark matter creates gravitational lensing effects that distort the images of more distant galaxies. Filaments connect the nodes. These are elongated structures, highways of galaxies stretching across hundreds of millions of light years. They're thinner than nodes, but much longer, creating the threads of the cosmic web. Matter in filaments is flowing toward the nearest node, falling along the gravitational gradient. New galaxies form within filaments as gas cools and condenses. Existing galaxies merge, building up mass as they travel toward the cluster. Sheets, also called walls, are two-dimensional structures where multiple filaments intersect or run parallel to each other. Finding something 10 billion light-years long isn't easy. You can't just point a telescope at the sky and see it directly. The structure is too large, too diffuse, spread across too much of the sky and too much cosmic time. Detecting massive structures like the Hercules Corona Borealis Great Wall requires sophisticated techniques, careful analysis, and the combination of multiple types of observations. Let me walk you through how astronomers actually do this. The fundamental tool is the redshift survey. This is the workhorse of large-scale structure studies, the method that has revealed most of what we know about the cosmic web. Here's how it works. When you look at a distant galaxy, the light you see has been traveling through space for millions or billions of years. During that journey, the space through which the light was traveling has been expanding. This expansion stretches the light's wavelength, shifting it toward the red end of the spectrum. The farther away the galaxy is, the more the space has expanded during the light's journey, and the larger the redshift. By measuring the redshift of a galaxy, you can determine its distance. The relationship between redshift and distance is well established, derived from our understanding of how the universe expands. It's not perfectly linear. The relationship changes depending on the properties of dark energy and the overall geometry of the universe, but it's calculable. So astronomers point their telescopes at galaxies, collect their light, spread that light into a spectrum showing all the different wavelengths present, and measure how much the light has been redshifted. From that measurement, they calculate the distance. Do this for one galaxy, and you know where one galaxy is. Do it for 1,000,000 galaxies, and you have a three-dimensional map of a significant volume of the universe. Plot those 1,000,000 galaxies as points in space, with their positions on the sky giving you 2 coordinates and their distances giving you the third, and the cosmic web appears. You see clusters where many galaxies are close together. You see filaments where galaxies are strung out in elongated chains. You see voids where almost no galaxies appear. The structure reveals itself through the distribution of points. The Sloan Digital Sky Survey is one of the most successful redshift surveys ever conducted. It has measured distances to millions of galaxies across about a third of the sky. The data from SDSS has revolutionized our understanding of large-scale structure, revealing the cosmic web in exquisite detail, and discovering structures like the Sloan Great Wall. But redshift surveys have limitations. They're time-consuming because you need to collect enough light from each galaxy to measure its spectrum. For faint, distant galaxies, this can take hours of observation time per galaxy. They're also limited by the sensitivity and field of view of the telescope. You can only observe so many galaxies per night. This is where other techniques become valuable. Photometric surveys are faster than spectroscopic surveys. Instead of measuring the full spectrum of each galaxy, photometric surveys just measure the brightness of galaxies in several different color filters. By comparing the brightness in different colors, you can estimate the redshift without needing a full spectrum. This is less precise than spectroscopic measurement, but it's much faster, allowing you to survey far more galaxies in the same amount of time. The Dark Energy Survey used photometric techniques to map hundreds of millions of galaxies. The upcoming Vera Rubin Observatory will use similar methods to catalog billions of galaxies, creating the largest three-dimensional map of the universe ever made. Gamma-ray burst surveys, which is how the Hercules Corona Borealis Great Wall was discovered, work differently. Gamma-ray bursts are extremely bright, temporary events. When a massive star collapses into a black hole, it can produce a gamma-ray burst that's visible across billions of light-years. These bursts last only seconds to minutes, but during that time, they're the brightest sources of gamma rays in the universe. By detecting gamma-ray bursts and measuring their redshifts, usually through follow-up observations of the afterglow in visible or infrared light, astronomers can map where these bursts occur. And since gamma-ray bursts are associated with the deaths of massive stars, they trace the distribution of star-forming galaxies across cosmic time. The SWIFT satellite, launched in 2004, has been detecting and characterizing gamma-ray bursts for nearly 2 decades. The Fermi Gamma-Ray Space Telescope, launched in 2008, has also contributed significantly to this effort. These satellites detect bursts, measure their positions on the sky, and alert ground-based telescopes to observe the afterglows and measure redshifts. When Istvan Balaz and his colleagues analyzed the distribution of gamma-ray bursts, they were looking for clustering, regions where bursts were more common than average, and they found an enormous clustering stretching across 10 billion light-years, the signature of the Hercules Corona Borealis Great Wall. X-ray surveys detect the hot gas that fills galaxy clusters. This gas, heated to tens of millions of degrees by gravitational compression, emits X-rays that can be detected by space-based X-ray telescopes. By mapping X-ray emission across the sky, astronomers can find galaxy clusters and trace the connections between them. The ROSAT satellite, in the 1990s, conducted the first all-sky X-ray survey, cataloging thousands of galaxy clusters. More recent missions like Chandra, XMM Newton, and Eros-Sitter have extended this work, finding fainter and more distant clusters and mapping the structure of the cosmic web in X-rays. X-ray observations are particularly valuable for studying the intra-cluster medium, the hot gas between galaxies in clusters. This gas contains more mass than all the galaxies in the cluster combined, and its properties tell us about the cluster's history, whether it's been recently disturbed by a merger, how much energy has been injected by supermassive black holes, and how the cluster is connected to the surrounding filaments. Gravitational lensing provides yet another window into large-scale structure. When light from distant galaxies passes near massive structures like galaxy clusters or filaments, it's bent by gravity. This bending distorts the images of background galaxies, stretching them into arcs or rings in extreme cases, or creating subtle shape distortions in less extreme cases. By measuring these distortions across many background galaxies, astronomers can map the distribution of mass in the foreground, including dark matter that doesn't emit light. This reveals the scaffolding of the cosmic web directly, showing where dark matter filaments stretch between clusters, where massive concentrations create strong lensing, and where voids contain very little mass. Weak gravitational lensing surveys measure tiny shape distortions in hundreds of millions of galaxies. The signal from any individual galaxy is too small to detect reliably, but statistically, averaging over many galaxies, the effect of foreground mass concentrations becomes clear. This technique is revealing the dark matter distribution of the cosmic web in unprecedented detail. All of these techniques are complementary. Redshift surveys show you where galaxies are. Gamma-ray burst surveys show you where massive stars are dying. X-ray surveys show you where hot gas concentrates. Gravitational lensing shows you where mass concentrates regardless of whether it's visible. By combining data from multiple surveys, using different techniques, astronomers can build a comprehensive picture of large-scale structure. They can identify filaments, measure their properties, trace their connections, and understand how they fit into the broader cosmic web. For the Hercules Corona Borealis Great Wall, the discovery came primarily from gamma-ray burst data, but confirming that discovery, understanding what the structure actually is, and measuring its properties requires follow-up observations using other techniques. Astronomers need to map the galaxies in that region of space using redshift surveys, look for X-ray emission from clusters within the structure, and measure the mass distribution using gravitational lensing. This is the slow, careful work of modern cosmology. A discovery is announced based on one type of observation. Then other astronomers follow up with different observations to confirm, refine, and expand our understanding. Over time, a consensus emerges about what's real and what's artifact, what's significant, and what's coincidence. In the case of the Hercules Corona Borealis Great Wall, this process is still ongoing. The structure was announced in 2013, but questions remain about whether it's truly a single coherent filament or a chance alignment of separate structures. Further observations are needed to settle the question definitively. But that's how science works. We observe, we analyze, we question, we follow up. Gradually, our understanding improves. The picture becomes clearer. And even when we can't answer every question immediately, the process of asking and investigating moves us forward. To understand how the Hercules Corona Borealis Great Wall was discovered, we need to understand gamma-ray bursts themselves. These are some of the most violent events in the universe, and they become powerful tools for mapping cosmic structure. A gamma-ray burst begins with a massive star, at least 20 or 30 times the mass of our Sun. Stars this large burn through their nuclear fuel very quickly, perhaps living only a few million years compared to the 10 billion-year lifespan of our Sun. When they exhaust their fuel, they die catastrophically. The core of the star collapses in less than a second, compressing matter to densities exceeding that of an atomic nucleus. If the star is massive enough, the collapse doesn't stop. The core breaks through the resistance of quantum pressure and continues collapsing, forming a black hole. As the core collapses, the outer layers of the star fall inward, then rebound outward in a supernova explosion. But in the cases that produce gamma-ray bursts, something additional happens. The newly formed black hole starts pulling in matter from the surrounding debris, forming an accretion disk of material spiraling inward at nearly the speed of light. Some of this infalling matter doesn't make it into the black hole. Instead, it's redirected into narrow jets shooting out from the poles of the accretion disk. These jets are accelerated to velocities within a fraction of a percent of the speed of light. They punch through the collapsing star and emerge into space, carrying enormous amounts of energy. The jets are narrow, typically only a few degrees wide, like a pair of searchlight beams emanating from the dying star. If one of those beams happens to be pointed toward Earth, we detect it as a gamma-ray burst. The gamma rays we detect are produced by multiple processes. Electrons accelerated to extreme energies in the jet spiral around magnetic field lines, emitting synchrotron radiation at gamma-ray wavelengths. The jet interacts with surrounding material, creating shocks that further accelerate particles and produce more gamma rays. The result is an intense flash of gamma-ray emission, lasting anywhere from a fraction of a second to several minutes. During this brief flash, the gamma-ray burst can be brighter than everything else in the universe combined. For those few seconds, it outshines all the stars in all the galaxies within billions of light-years. A single dying star, in its final moments, becomes the brightest object in the cosmos. After the initial gamma-ray emission fades, an afterglow remains. The jet continues to plow through surrounding material, creating a shock wave that glows in X-rays, visible light, and radio waves. This afterglow fades over hours to weeks, but during that time, it can be observed by ground-based telescopes. The afterglow is crucial for determining the distance to the gamma-ray burst. When a burst is detected by a satellite, the satellite's position and direction are immediately sent to ground-based telescopes around the world. These telescopes slew to the position and begin observing the afterglow, collecting enough light to create a spectrum. The spectrum shows emission and absorption lines from elements in the host galaxy where the burst occurred. These lines are redshifted by the expansion of the universe, and by measuring that redshift, astronomers can determine how far away the burst is. Most gamma-ray bursts occur at enormous distances. They're visible from billions of light-years away, which means we're seeing bursts that occurred billions of years ago, when the universe was much younger. The light from these bursts has been traveling through space for most of cosmic history, finally arriving at our satellites and telescopes to be detected and analyzed. Because gamma-ray bursts are so bright and so distant, they're excellent tracers of cosmic structure. They tell us where massive stars are forming and dying across billions of light-years of space and billions of years of cosmic time. When Istvan Balázs and his colleagues were studying gamma-ray bursts, they weren't initially looking for large-scale structure. They were studying the bursts themselves, trying to understand their properties, their origins, their diversity. But as part of that work, they catalogued the positions and distances of hundreds of bursts. And when they plotted those positions in three-dimensional space, they noticed something. The bursts weren't uniformly distributed. There was clustering. Certain regions of space had many more bursts than average, while other regions had very few. This clustering made sense. Gamma-ray bursts occur in star-forming galaxies, and star-forming galaxies aren't uniformly distributed. They're concentrated in filaments and clusters of the cosmic web, so gamma-ray bursts should show the same concentration. But the clustering Ballas found was more extreme than expected. There was a massive excess of gamma-ray bursts in a particular region of the sky, stretching across an enormous range of distances. When they calculated the extent of this clustering, they found it spanned about 10 billion light-years. To determine whether this clustering was statistically significant or just a random fluctuation, they performed careful analysis. They calculated the probability that such a clustering could occur by chance if gamma-ray bursts were randomly distributed through space. The probability was extremely low. The clustering was significant, at the 5 sigma level or higher, meaning there was less than a 1 in a million chance that it was a random fluctuation. This was strong statistical evidence for a real structure. But statistical evidence isn't the same as direct observation. The challenge with using gamma-ray bursts to trace structure is that the bursts themselves are rare events. You're not mapping the galaxies directly. You're mapping where massive stars are dying and inferring from that where galaxies are located. This introduces uncertainty. Maybe the clustering of gamma-ray bursts doesn't reflect an underlying clustering of galaxies. Maybe there's some other effect at play, some bias in how bursts are detected or how their distances are measured, that creates the appearance of structure where none exists. This is why the Hercules Corona Borealis Great Wall remains somewhat controversial. The gamma-ray burst data shows strong clustering, but follow-up observations using other techniques haven't definitively confirmed that this clustering corresponds to a single coherent filament of galaxies. Some studies have found evidence for enhanced galaxy density in the same region where the gamma-ray bursts cluster. Others have found no significant excess. The debate continues, and more observations are needed to resolve the question. But regardless of whether the Hercules Corona Borealis Great Wall is ultimately confirmed as a single structure, the gamma-ray burst method has proven its value. It's shown that these violent explosions can be used to map cosmic structure across distances and timescales that are difficult to probe using other methods. Future gamma-ray burst missions will detect even more bursts, catalog them more completely, and measure their distances more precisely. This will allow for more detailed mapping of the cosmic web using gamma-ray bursts as tracers, potentially revealing structures that would be invisible through other techniques. And that's the beauty of having multiple methods. Each technique has its strengths and limitations. By combining them, by using gamma-ray bursts and galaxy surveys and X-ray observations and gravitational lensing all together, we build a more complete picture of the universe than any single method could provide. The Hercules Corona Borealis Great Wall didn't appear out of nowhere. It's part of a progression of discoveries, each one revealing larger structures than the previous, each one pushing our understanding of what the universe can create. Let's walk through the history of these discoveries, the structures that held the record for largest known structure before the Hercules Corona Borealis Great Wall potentially claimed that title. The first Great Wall was discovered in 1989 by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. They were conducting a redshift survey, measuring the distances to galaxies in a thin slice of the sky, essentially creating a two-dimensional slice through the three-dimensional universe. What they found shocked them. Instead of galaxies being randomly scattered through space, they saw a massive sheet of galaxies stretching across their entire survey region. This structure, which they called the CFA2 Great Wall after their institution, was about 500 million light-years long, 300 million light-years wide, and only about 15 million light-years thick. Imagine a wall 500 million light-years long, but only 15 million light-years thick. It's like a cosmic sheet, a membrane of galaxies forming a boundary around an enormous void. The discovery of the CFA2 Great Wall was revolutionary because it was the first clear evidence that the universe has structure at scales of hundreds of millions of light-years. Prior to this, astronomers had known about galaxy clusters, and even some larger groupings, but nothing on this scale. The wall appeared as a prominent feature in the famous stickman diagram from the CFA redshift survey, a plot showing how galaxies are distributed in their slice of the universe. The stick figure shape came from the arrangement of structures, and one of the stick figure's arms was the CFA2 Great Wall. For more than a decade, this was the largest known structure in the universe. It set a benchmark and raised questions. How did something this large form? What does its existence tell us about the initial conditions in the early universe? Are there even larger structures waiting to be discovered? The answer to that last question turned out to be yes. In 2003, the Sloan Digital Sky Survey discovered an even larger structure. The Sloan Great Wall stretches approximately 1.37 billion light-years across space. It's nearly 3 times the length of the CFA2 Great Wall, containing thousands of galaxies arranged in a complex network of filaments and clusters. The Sloan Great Wall is located about 1 billion light-years from Earth. When we observe it, we're seeing light that left when the universe was about 93% of its current age, a relatively recent time in cosmic terms. What makes the Sloan Great Wall particularly impressive is its complexity. It's not a simple sheet like the CFA2 Great Wall. It's more like a network, with multiple filaments intersecting and connecting, clusters scattered throughout, and voids carved out between the dense regions. It's a microcosm of the cosmic web, a portion of the larger structure that happens to be oriented in a way that makes it appear as a coherent entity from our vantage point. The discovery of the Sloan Great Wall came from the massive data set of the Sloan Digital Sky Survey, which had measured redshifts for hundreds of thousands of galaxies. When astronomers plotted these galaxies in three-dimensional space, the Sloan Great Wall emerged as a prominent feature stretching across a significant fraction of the surveyed volume. For over a decade, from 2003 to 2013, the Sloan Great Wall held the record as the largest known structure. Its existence pushed the boundaries of what cosmologists thought was possible. Structures this large were at the edge of what standard cosmological models predicted could form, given the age of the universe and the laws of physics. But the Sloan Great Wall wasn't alone. Other large structures were being discovered around the same time or shortly after. The huge LQG, or Huge Large Quasar Group, was discovered in 2012. Large quasar groups are collections of quasars, extremely bright active galactic nuclei powered by supermassive black holes that are relatively close together in space. The huge LQG contains 73 quasars spread across a region about 4 billion light-years in extent. This structure is controversial because quasar groups are different from galaxy filaments or walls. Quasars are rare objects, and it's not clear that their clustering necessarily reflects an underlying structure in the distribution of galaxies. Some astronomers argue that the huge LQG is a real structure, a massive concentration of matter. Others suggest it might be a statistical coincidence, a random clustering that appears significant but doesn't represent a coherent physical structure. The giant GRB ring, discovered in 2015, is another controversial structure. This is a ring-shaped distribution of gamma-ray bursts, about 5 billion light-years in diameter. Like the Hercules Corona Borealis Great Wall, it was found by analyzing the distribution of gamma-ray bursts across the sky. The giant GRB ring is puzzling. Ring-shaped structures aren't predicted by standard cosmological models. The cosmic web produces filaments, sheets, and voids, but not rings. If the giant GRB ring is real, it would suggest some unusual physics or initial conditions. But like the Hercules Corona Borealis Great Wall, questions remain about whether it's truly a coherent structure or an artifact of the data. In 2017, astronomers discovered the Saraswati supercluster, a massive concentration of galaxy clusters about 652 million light-years across and containing about 400 galaxies. It's located about 4 billion light-years from Earth. The Saraswati supercluster is one of the most massive structures known, with a total mass estimated at about 20 million billion times the mass of our Sun. It's arranged in a wall-like structure, with clusters aligned along filaments forming a coherent whole. What makes Saraswati particularly interesting is its age. At 4 billion light-years away, we're seeing it as it was when the universe was about 10 billion years old. That's relatively early in cosmic history. The fact that such a massive structure had already assembled by that time puts constraints on models of structure formation. In 2020, astronomers discovered the South Pole Wall, a massive filament stretching at least 1.4 billion light-years across space. It's located about 500 million light-years from Earth, relatively nearby in cosmic terms, but it had been hidden from view behind the plane of the Milky Way. The plane of our galaxy contains dust and gas that blocks visible light from more distant objects. This creates a region of the sky called the zone of avoidance, where galaxies are difficult to observe. The South Pole Wall lies within this zone, which is why it went undetected for so long despite being relatively close. Astronomers found it by using alternative methods that aren't blocked by Milky Way dust, mapping the motions of galaxies through their gravitational effects rather than observing them directly. The South Pole Wall appears as a massive filament connecting several known galaxy clusters and superclusters, a structure that's been there all along but hidden behind our galaxy's obscuring material. Each of these discoveries revealed something new about the universe. The CFA2 Great Wall showed us that structure exists at scales of hundreds of millions of light-years. The Sloan Great Wall extended that to over 1 billion light-years. The various quasar groups and gamma-ray burst structures, controversial though they may be, pushed the boundaries even further. And then came the Hercules Corona Borealis Great Wall in 2013, potentially spanning 10 billion light-years, roughly 10 times the size of the Sloan Great Wall, and approaching 1/10 the diameter of the observable universe itself. Each step in this progression challenged cosmological models. Each new record holder raised the question, is there a maximum size for cosmic structures? And if so, what determines that maximum? This brings us to one of the most interesting questions in cosmology, the cosmological principle and its limits. The cosmological principle is one of the fundamental assumptions of modern cosmology. It states that the universe is homogeneous and isotropic when viewed at sufficiently large scales. Let me break down what that means and why the Hercules Corona Borealis Great Wall challenges it. Homogeneous means the same everywhere. If you pick any location in the universe and measure the average density of matter within a large enough volume around that location, you should get the same answer regardless of which location you picked. There's no special place, no center, no edge. Everywhere is fundamentally the same when you average over large enough scales. Isotropic means the same in all directions. If you stand at any location and look around, the universe should appear statistically similar in every direction. Again, this is after averaging over large enough volumes. Any individual direction might show some structure, clusters here, voids there, but when you average over all directions, everything should balance out. The cosmological principle has been a cornerstone of our understanding of the universe since the 1930s. It's supported by observations of the cosmic microwave background, the afterglow of the Big Bang, which appears remarkably uniform across the entire sky. It's also philosophically appealing because it suggests we don't live in a special place. Our location in the universe is typical, representative of the universe as a whole. But the cosmological principle is an idealization. It doesn't claim that the universe is perfectly smooth at all scales. Obviously, it's not. We see stars, galaxies, clusters, filaments. There's structure everywhere we look. The principle only claims that when you zoom out far enough, when you average over large enough scales, the lumpiness averages away and you're left with uniformity. The question is, how large is large enough? In the 1980s, cosmologists calculated a characteristic scale called the homogeneity scale, or the end of greatness. This is the scale beyond which structure should fade away, and the universe should appear uniform. Based on the observed density fluctuations in the early universe, and our understanding of how gravity amplifies those fluctuations, this scale was estimated to be around 1.2 billion light-years. What this means is that if you average the matter density over spheres 1.2 billion light-years across, placed randomly throughout the universe, the variation from one sphere to another should be small. The universe should look homogeneous at this scale and above. But the Hercules Corona Borealis Great Wall, at 10 billion light-years across, is much larger than 1.2 billion light-years. It's so large that it shouldn't exist if the cosmological principle and the associated homogeneity scale are correct. This creates a tension. Either our calculations of the homogeneity scale are wrong, or the cosmological principle breaks down at larger scales than we thought, or the Hercules Corona Borealis Great Wall isn't actually a coherent structure, and its apparent size is an illusion. The third possibility is real. Remember, the Hercules Corona Borealis Great Wall was discovered through gamma-ray burst clustering, not through direct galaxy mapping. It's possible that what appears as a single 10 billion light-year structure is actually several smaller structures that happen to align along our line of sight. From Earth, if you have 3 separate filaments at different distances, but all in roughly the same direction, they might appear to form a single elongated structure. Only by mapping the galaxies directly and confirming that they're physically connected can you determine whether it's truly one structure or an apparent alignment. This is why the Hercules Corona Borealis Great Wall remains controversial. The gamma-ray burst data shows a clear excess. The statistical significance is high, but the follow-up observations needed to confirm the structure's reality and measure its properties are difficult and time-consuming, and they haven't yet provided a definitive answer. But let's assume for the moment that the structure is real, that it's truly a single coherent filament, 10 billion light-years long. What would that mean for the cosmological principle? It would mean that the homogeneity scale is larger than we thought. Perhaps instead of 1.2 billion light-years, it's 10 billion or 15 billion light-years. You'd need to average over scales approaching the size of the observable universe before the lumpiness averages away, and you see uniformity. This wouldn't necessarily disprove the cosmological principle entirely. The principle could still be valid. We just need to revise our understanding of what sufficiently large scales means. But it would be a significant revision, one that would require us to rethink aspects of cosmological theory. Alternatively, the existence of structures this large might suggest that the cosmological principle is only approximately true, valid as a useful simplification, but not as a precise description of reality. Perhaps the universe is homogeneous on average, but with larger fluctuations around that average than we expected. Or perhaps the cosmological principle is simply wrong at some level. Perhaps the universe does have preferred directions or special locations when viewed at the largest scales. This would be a radical revision of cosmology, but it's not impossible. Science has revised fundamental principles before when observations demanded it. The tension between the cosmological principle and large structures like the Hercules Corona Borealis Great Wall is an active area of research. Cosmologists are working to understand whether structures this large are compatible with our models or whether they require new physics. One important consideration is cosmic variance. The observable universe is finite. We can only see a limited volume of space, and the structures within that volume are the result of random fluctuations in the early universe. It's possible, just by chance, that our observable volume happens to contain unusually large structures. If you only sample a small piece of a random distribution, that sample might not be representative of the whole. Maybe the universe beyond our cosmic horizon is more uniform, and we just happen to live in a region with larger than typical structures. This is impossible to verify directly, because we can't observe beyond our cosmic horizon, but we can use statistics and simulations to estimate the probability. If structures like the Hercules Corona Borealis Great Wall should appear in, say, 1 out of every 100 observable volumes due to random chance, then finding one in our volume isn't particularly surprising. Current simulations suggest that structures approaching this size are rare but not impossible. They appear in some simulated universes, but not others, depending on the specific random fluctuations in each simulation. Finding one in our observable universe might simply be luck. But if we keep finding structures at the edge of or beyond what our models predict, if the Hercules Corona Borealis Great Wall is just the first of many similarly large structures, then we'd have to conclude that our models are systematically underestimating the amount of structure at large scales. The cosmological principle is testable through observations. If the universe really is homogeneous at large enough scales, then when we measure the matter density in different regions billions of light-years across, we should get the same answer everywhere, within some small statistical variation. Future surveys will test this directly. The upcoming Vera Rubin Observatory, the Euclid mission, the Nancy Grace Roman Space Telescope, all will map the distribution of galaxies across enormous volumes with unprecedented precision. They'll measure whether the universe really does become smooth at large scales, or whether structure persists even at the largest scales we can observe. If the cosmological principle holds, these surveys will confirm it with high precision. If it doesn't, these surveys will reveal exactly how and at what scale it breaks down. This is how science progresses. We start with assumptions based on limited data and philosophical reasoning. We make predictions based on those assumptions. We collect more data and test those predictions. When the data contradicts the assumptions, we revise them. Over time, our understanding improves, becoming more accurate, more refined, more closely aligned with reality. The Hercules Corona Borealis Great Wall, whether it's ultimately confirmed as a single structure or reinterpreted as something else, has already served a valuable purpose. It's forced us to think more carefully about the cosmological principle, about the homogeneity scale, about what we mean when we say the universe is uniform at large scales. And it's reminded us that the universe is under no obligation to conform to our expectations. When astronomers claim to have discovered a structure like the Hercules Corona Borealis Great Wall, they're not just saying, "We saw some clustering in the data." They're making a statistical argument that the clustering is real, significant, and unlikely to be a random fluctuation. Let's talk about how that argument works and what it means. Statistical significance is how we distinguish real patterns from noise. Imagine you flip a coin 100 times and get 60 heads and 40 tails. Is the coin unfair, biased toward heads, or did you just get lucky? The coin might be perfectly fair, and the 6-0-4-0 split might have occurred by random chance. To answer this question rigorously, you calculate the probability that a fair coin would produce a result at least this extreme. If that probability is very low, say less than 5%, then you have evidence that the coin might be biased. The lower the probability, the stronger the evidence. In particle physics and astronomy, the standard threshold for claiming a discovery is 5 sigma, which corresponds to a probability of less than 1 in 3.5 million that the result occurred by random chance. This is a very stringent requirement, chosen specifically because data can be noisy and patterns can appear where none exist. For the Hercules Corona Borealis Great Wall, the question is whether the clustering of gamma-ray bursts in that region of the sky could have occurred by random chance if gamma-ray bursts were actually uniformly distributed through space. To answer this, you need a statistical model. You start by assuming that gamma-ray bursts are distributed uniformly, with no underlying structure. This is called the null hypothesis. Then you calculate the probability of seeing a clustering as extreme as what was observed if the null hypothesis were true. The calculation is complex because you need to account for various factors: the total number of gamma-ray bursts observed, The volume of space surveyed. The fact that you're looking for clustering in all possible regions, not just one specific region you chose in advance. This last point is important because if you search through enough data, you'll inevitably find some apparent pattern just by chance. This is called the look elsewhere effect, or the multiple comparisons problem. If you flip a coin 100 times and look for any streak of 5 heads in a row somewhere in those 100 flips, you're much more likely to find one than if you specifically predicted in advance that flips 23 through 27 would all be heads. To account for this, the statistical analysis for the Hercules Corona Borealis Great Wall had to consider not just the probability of finding clustering in that specific location, but the probability of finding clustering of that magnitude anywhere in the surveyed sky. The analysis showed that the clustering was significant at the 5 sigma level or higher. This means the probability of seeing such a clustering by random chance is less than 1 in 3.5 million. That's strong evidence that the clustering is real, not a statistical fluke. But statistical significance isn't the same as certainty. There are several caveats. First, the calculation depends on the assumed null hypothesis. If gamma-ray bursts aren't actually uniformly distributed for reasons unrelated to large-scale structure, then the null hypothesis is wrong and the statistical significance calculation is meaningless. For example, if there's a bias in how gamma-ray bursts are detected or measured that makes them appear to cluster even when they don't, the statistical test wouldn't catch this. It would only tell you that the clustering is unlikely to arise from random chance, not that it's unlikely to arise from systematic errors or biases. Second, statistical significance tells you that a pattern exists, but it doesn't tell you what that pattern represents. The gamma-ray bursts clearly cluster more than you'd expect by random chance. But does that clustering represent a single coherent structure, or multiple structures that happen to be near each other, or some artifact of how the data was collected and analyzed? This is why follow-up observations are essential. Statistical significance tells you that something interesting is happening and worth investigating further. But only detailed follow-up, mapping the galaxies directly, measuring the mass distribution, checking for connections between different parts of the structure, can confirm what that something actually is. Third, even 5 sigma significance isn't absolute proof. 1 in 3.5 million is an extremely low probability, but it's not zero. If astronomers search through enough data looking for structures, they'll occasionally find apparent 5 sigma detections that are actually just statistical flukes. This is rare, but it happens. This is why reproducibility is important in science. If one team finds a 5 sigma detection of a structure, and then other teams using independent data and methods find the same structure, confidence increases dramatically. Multiple independent confirmations make it much less likely that the result is a statistical accident. For the Hercules Corona Borealis Great Wall, we're in an intermediate state. The original detection was statistically significant. Some follow-up studies have found evidence supporting the structure's existence. Others have found no significant excess of galaxies in the same region. The situation is still being resolved. Let me explain how the statistical analysis for cosmic structures typically works in more detail. You start with a catalogue of objects. For the Hercules Corona Borealis Great Wall, this was a catalogue of gamma-ray bursts, with measured positions on the sky and measured redshifts indicating their distances. You plot these objects in 3-dimensional space, 2 coordinates for position on the sky and 1 for distance. Then you look for overdensities, regions where objects are more concentrated than the average. To determine whether an overdensity is significant, you compare it to what you'd expect from random chance. You might run Monte Carlo simulations, creating thousands of fake catalogues where objects are distributed randomly but with the same total number and the same distribution of distances as the real catalogue. Then you search each fake catalogue for overdensities and record the strongest one you find. After running thousands of simulations, you have a distribution showing how strong the overdensities in random catalogues tend to be. You can then compare the overdensity found in the real data to this distribution. If the real overdensity is much stronger than what typically appears in the random catalogs, that's evidence of significance. For the Hercules Corona Borealis Great Wall, this analysis showed that the observed clustering was much stronger than what appeared in the random catalogs. The probability of getting such a strong clustering by chance was calculated to be less than 1 in several million, depending on exactly how the analysis was done. This is what we mean by 5 sigma significance. The Greek letter sigma, psi, represents the standard deviation in a distribution. A 5 sigma result is one that deviates from the mean by 5 standard deviations, which for a normal distribution corresponds to a probability of about 0.00006%, or about 1 in 1.7 million for a one-tailed test and 1 in 3.5 million for a two-tailed test. In practice, cosmic structure distributions aren't perfectly normal, so the exact probability depends on the specific distribution, but the principle is the same. 5 sigma means extremely unlikely to occur by random chance. But again, unlikely doesn't mean impossible, and statistical significance doesn't eliminate all possible sources of error. It only tells you that random chance is an unlikely explanation. This is why the scientific process doesn't stop with a single detection. The Hercules Corona Borealis Great Wall announcement in 2013 was the beginning of the story, not the end. Since then, other astronomers have been working to confirm or refute the discovery using independent methods. Some have conducted galaxy surveys in the same region of the sky, looking for an excess of galaxies that would indicate a real structure. Some have looked for X-ray emission from clusters within the supposed structure. Some have reanalyzed the gamma-ray burst data, using different statistical methods to check whether the significance holds up. This process is ongoing. Science isn't a single event where truth is revealed. It's a gradual accumulation of evidence, a back and forth between different groups using different methods, a slow convergence towards consensus. Sometimes this process confirms the initial discovery, as happened with the Sloan Great Wall, which has been confirmed by multiple independent observations and is now accepted as a real structure. Sometimes the process refutes the initial discovery, showing that what appeared significant was actually an artifact or misinterpretation. And sometimes, as with the Hercules Corona Borealis Great Wall, the process takes time and the final answer isn't yet clear. But this uncertainty is a feature of science, not a bug. It's what keeps us honest, what prevents us from jumping to conclusions, what ensures that our understanding is built on solid evidence rather than wishful thinking. The statistical significance of the Hercules Corona Borealis Great Wall discovery tells us that there's something real in the data worth investigating. Whether that something is a single coherent structure 10 billion light-years long, or something else, remains to be fully determined. To understand how structures like the Hercules Corona Borealis Great Wall form, we need to talk about dark matter. This invisible substance makes up about 85% of all matter in the universe, and it's absolutely essential to understanding how the cosmic web came to be. Let me start with what we know about dark matter, how we discovered it, and why it matters for structure formation. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. The only way we know it exists is through its gravitational effects on things we can see. The first evidence for dark matter came in the 1930s, when Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies about 321 million light-years from Earth. Zwicky measured how fast the galaxies in the cluster were moving by analyzing the Doppler shifts in their light. What he found puzzled him. The galaxies were moving too fast. When you have a gravitationally bound system like a galaxy cluster, there's a relationship between the mass of the system and the velocities of the objects within it. More massive systems have stronger gravity, which allows objects to orbit faster without escaping. Zwicky calculated how much mass the Coma cluster should have, based on the light from all its galaxies. Then he calculated how much mass it would need to have to keep those galaxies bound at the velocities he measured. The second number was about 400 times larger than the first. Either the galaxies were about to fly apart, which seemed unlikely because the cluster appeared stable, or there was much more mass present than could be accounted for by visible matter. Zwicky called this missing mass dark matter, and his observation was largely ignored for decades. In the 1970s, Vera Rubin and Kent Ford made observations that would eventually force astronomers to take dark matter seriously. They measured rotation curves of spiral galaxies, plotting how fast stars orbit at different distances from the galactic center. In a spiral galaxy, most of the visible matter, the stars, is concentrated toward the center. If this visible matter were all the mass present, you'd expect stars farther from the center to orbit more slowly, just as outer planets in our solar system orbit the sun more slowly than inner planets. But that's not what Rubin and Ford found. Instead, they found that stars far from the galactic center were orbiting just as fast as stars closer in. The rotation curves were flat rather than declining. This implied that there was additional mass extending far beyond the visible disk of the galaxy, creating a gravitational field strong enough to keep those outer stars moving at high speeds. This additional mass had to be dark because telescopes couldn't see it, and it had to be massive because only a substantial amount of mass could produce the observed gravitational effects. Since then, evidence for dark matter has accumulated from many independent sources. Gravitational lensing shows that galaxy clusters contain far more mass than can be accounted for by visible matter. The cosmic microwave background has tiny fluctuations that can only be explained if dark matter exists and dominates the matter content of the universe. Computer simulations of structure formation only match observations when dark matter is included. All of these different lines of evidence point to the same conclusion. About 85% of the matter in the universe is dark matter, and only about 15% is the ordinary matter made of atoms that we're familiar with. Now, here's why dark matter matters for structure formation. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, but not perfectly uniformly. There were tiny variations in density, perhaps 1 part in 100,000. Some regions were slightly denser than average, others were slightly less dense. Gravity amplifies these variations. Dense regions attract matter from their surroundings, becoming denser. Less dense regions lose matter to their neighbors, becoming less dense. Over time, this process creates the cosmic web, with matter flowing from voids into filaments and from filaments into clusters. But here's the crucial point. If only ordinary matter existed, this process would work too slowly to create the structures we see today. Ordinary matter in the early universe was hot, moving at high speeds. This thermal motion resists gravitational collapse. It takes a long time for gravity to overcome this resistance and pull matter together. Dark matter changes everything. Dark matter doesn't interact with light, which means it doesn't experience radiation pressure. It doesn't heat up when compressed. It doesn't have thermal motion in the same way ordinary matter does. This means dark matter can begin collapsing into structures much earlier than ordinary matter. In the early universe, while ordinary matter was still hot and resisting collapse, dark matter was already clumping together under gravity, forming the first halos, the first seeds of structure. These dark matter halos created gravitational wells, regions where the gravitational pull was stronger than average. Once these dark matter halos formed, ordinary matter could fall into them. The gravity of the dark matter helped ordinary matter overcome its thermal resistance. Gas fell into the dark matter halos, cooled, condensed, and formed the first stars and galaxies. Without dark matter, structure formation would have taken much longer. The universe might not have had time to form galaxies, let alone galaxy clusters and filaments, within its 13.8 billion year history. The cosmic web we observe today is a direct consequence of dark matter's existence and properties. Think of dark matter as the scaffolding on which the cosmic web is built. The filaments of the cosmic web are primarily dark matter filaments. The galaxy clusters are embedded in massive dark matter halos. The visible matter, the galaxies and gas and stars, traces the underlying dark matter distribution, but only makes up a small fraction of the total mass. When we observe structures like the Hercules Corona Borealis Great Wall, we're seeing the visible matter that's collected along dark matter filaments over billions of years. The structure exists because dark matter created the gravitational framework that allowed ordinary matter to flow along those paths and accumulate in those locations. Computer simulations of structure formation make this clear. Cosmologists can simulate the evolution of the universe from shortly after the Big Bang to the present day. They set up initial conditions matching what we observe in the cosmic microwave background, small density fluctuations distributed according to the predictions of inflation theory. Then they let the simulation run forward in time, calculating how gravity affects every particle. When you run these simulations with only ordinary matter, the results don't match observations. Structure forms too slowly, the cosmic web is too diffuse, galaxy clusters are too small. But when you include dark matter, making it about 85% of the total matter and giving it the properties we infer from observations, the simulations work. The cosmic web emerges naturally. Filaments stretch between clusters. Voids expand. The statistical properties of the simulated universe match the statistical properties of the real universe remarkably well. These simulations show dark matter halos forming first, hundreds of millions of years after the Big Bang, then ordinary matter falling into those halos and forming stars and galaxies. Then those galaxies growing through mergers and through accretion of material along filaments. Then clusters forming where multiple filaments intersect. The entire hierarchy of structure building up over billions of years. The largest structures, filaments like the Hercules Corona Borealis Great Wall, form last. They require the longest time to assemble because matter has to flow across the largest distances. But even these massive structures are held together by dark matter, the invisible gravitational glue that binds the cosmos. We still don't know what dark matter actually is. We know it has mass and exerts gravity. We know it doesn't interact with light. We know it's not made of atoms or any of the particles we're familiar with from everyday life. But beyond that, its nature remains mysterious. The leading candidates are weakly interacting massive particles, WIMPs, hypothetical particles that would have been produced in the early universe and that interact only through gravity and possibly the weak nuclear force. Experiments around the world are searching for WIMPs, trying to detect them directly through their rare interactions with ordinary matter. Other candidates include axions, very light particles proposed to solve a different problem in particle physics, but which might also constitute dark matter, and sterile neutrinos, heavy cousins of the familiar neutrinos that might have been produced in the early universe. Whichever of these turns out to be correct, or if dark matter is something else entirely, the gravitational effects are well established. Dark matter creates the framework of the cosmic web. It determines how structure forms, where galaxies collect, how filaments stretch across billions of light years. Understanding dark matter is essential to understanding the universe at the largest scales. And structures like the Hercules Corona Borealis Great Wall are direct evidence of dark matter's influence, monuments to the invisible substance that dominates the cosmos and makes possible everything we see. Understanding the universe at the largest scales requires more than observation alone. We need simulations, computer models that can evolve billions of particles over billions of years, showing us how the cosmic web grows from tiny seeds in the early universe to the massive structures we observe today. The most famous of these is the Millennium Simulation, and it represents one of humanity's most ambitious attempts to recreate the universe inside a computer. The Millennium Simulation was conducted in 2005 by an international team of astronomers led by the Max Planck Institute for Astrophysics in Germany. It tracked the evolution of more than 10 billion particles, representing dark matter, from shortly after the Big Bang to the present day, a span of more than 13 billion years of cosmic history. To give you a sense of the computational challenge involved, the simulation required more than 28 million processor hours on one of the world's most powerful supercomputers at the time. If you tried to run it on a standard desktop computer, it would take thousands of years to complete. The data generated filled hundreds of terabytes of storage, enough to store the entire text content of millions of books. The simulation started with initial conditions based on observations of the cosmic microwave background. The tiny temperature fluctuations in the CMB correspond to tiny density variations in the early universe, and these became the starting point for the simulation. Some regions were given slightly higher density, others slightly lower, matching the pattern observed in the real universe. Then the simulation let gravity do its work. Each of the 10 billion particles exerted gravitational force on every other particle within its neighborhood. The computer calculated these forces, updated the positions and velocities of all particles, advanced time by a small step, and repeated, over and over, billions of iterations, marching forward through cosmic time. What emerged was extraordinary. The simulation showed dark matter collecting into halos, small at first, then growing through mergers and accretion. It showed these halos, connecting along filaments as matter flowed from less dense regions toward denser ones. It showed the cosmic web emerging naturally from the initial conditions, and the laws of gravity, no special instructions needed, just matter responding to matter through gravitational attraction. The structures that formed in the Millennium simulation matched observations remarkably well. The statistical properties of galaxy clusters in the simulation, their abundance, their sizes, their distribution, all agreed with what astronomers observed in the real universe. The filaments had the right lengths and widths, the voids had the right sizes. The hierarchical pattern of structure, small halos merging to form larger ones, which merged to form larger ones still, matched the pattern inferred from observations. This agreement between simulation and observation is powerful evidence that we understand the basic processes of structure formation. We know the initial conditions from CMB observations. We know the laws of physics that govern how matter evolves. When we combine these in a simulation, we get a universe that looks like the real one. This suggests our theoretical framework is fundamentally correct. But the Millennium simulation had limitations. It only tracked dark matter, not ordinary matter, including gas, star formation, supernovae, black holes, and all the complex physics of how galaxies actually form, would have required far more computational power than was available. So the Millennium simulation showed where galaxies should form, the dark matter scaffolding, but not the galaxies themselves in detail. Later simulations addressed this. The Illustrasis simulation, completed in 2014, included detailed models of ordinary matter. It simulated gas cooling and heating, star formation, supernova explosions, supermassive black holes and their jets, all the astrophysics that shapes galaxies. The computational cost was enormous, even greater than the Millennium simulation, but the result was a simulated universe containing realistic-looking galaxies with properties matching observations. The Illustris TNG simulations, completed in 2018, extended this even further with improved physics and higher resolution. These simulations produced galaxies with realistic spiral arms, central bulges, and satellite galaxies. They showed how supermassive black holes regulate star formation in massive galaxies. They revealed how galaxies evolve over cosmic time, through mergers and through steady accretion of gas from the cosmic web. Each generation of simulations has become more sophisticated, incorporating more physics, tracking more particles, resolving smaller structures. And each generation has matched observations more closely, giving us greater confidence that we understand how the universe works. These simulations make predictions that can be tested. They tell us how many galaxy clusters should exist at different masses. They tell us how the cosmic web should evolve over time. They tell us what the largest structures should look like and how common they should be. And this brings us back to the Hercules Corona Borealis Great Wall. Do simulations predict that structures this large should exist? The answer is complicated. Structures approaching 10 billion light-years in length do appear in large cosmological simulations, but they're rare. In a typical simulation of a volume comparable to the observable universe, you might find one or two filaments this long, maybe none, depending on the specific random fluctuations in that particular simulation. This rarity makes sense. The largest structures form from the largest scale density fluctuations in the early universe, and the amplitude of fluctuations decreases as the scale increases. There's less variation at large scales than at small scales, which means extreme overdensities that could grow into structures like the Hercules Corona Borealis Great Wall are uncommon. The fact that we observe such a structure in our observable universe is not impossible according to simulations. It's unlikely, but not impossibly so. This is what we mean by cosmic variance. Different regions of the universe will have different realizations of the random fluctuations, and some regions will by chance have larger structures than others. But there's a caveat. The Hercules Corona Borealis Great Wall, if it's truly 10 billion light-years long, is at the extreme edge of what simulations typically produce. Finding such a structure in our relatively small observable volume is somewhat fortunate. It's not so unlikely that it disproves our models, but it is unusual enough to raise eyebrows and motivate careful scrutiny of both the observations and the theory. Other simulations have explored different aspects of cosmic structure. The Eagle simulations focused on forming realistic galaxies and understanding how feedback from stars and black holes affects galaxy properties. The Horizon AGN simulation emphasized the role of supermassive black holes in shaping galaxies and the cosmic web. The Bahamas simulation focused on the hot gas in galaxy clusters and how it traces the cosmic web. Each of these simulations approaches the problem differently, emphasizing different physics, making different approximations. But they all agree on the basic picture. Dark matter forms the scaffolding of the cosmic web. Ordinary matter flows along this scaffolding, collecting in filaments and clusters. Gravity drives the growth of structure, while cosmic expansion works against it. The result is the hierarchical cosmic web we observe, with structure on all scales from small halos to massive filaments. Simulations also allow us to look inside structures in ways we can't with observations. We can follow individual dark matter particles as they flow through the cosmic web. We can watch as galaxy clusters form through multiple mergers over billions of years. We can see how galaxies are transformed as they fall into clusters, stripped of their gas, their star formation quenched. One striking finding from simulations is that galaxies don't form in isolation. They form within the cosmic web, and their properties are shaped by their environment. Galaxies in dense clusters tend to be older, redder, with less active star formation. Galaxies in filaments tend to be younger, bluer, still forming stars. Galaxies in voids are often small and isolated. This makes sense. Clusters are where matter has been accumulating for the longest time. Galaxies there have already consumed most of their gas-forming stars. They've been stripped of additional gas by interactions with the hot intracluster medium. They're essentially finished forming. In contrast, galaxies in filaments are still being fed by gas flowing along the cosmic web. They're still growing, still forming stars, and galaxies in voids have less access to gas because the voids have been evacuated. They're small and isolated, evolving slowly. These predictions from simulations have been confirmed by observations. When astronomers map the properties of galaxies and compare them to their locations in the cosmic web, they find exactly these patterns. Environment matters for galaxy evolution, and simulations explain why. For structures like the Hercules Corona Borealis Great Wall, Simulations tell us that such filaments should contain a mix of galaxy populations. The densest clusters within the filament should have older, redder galaxies. The thinner sections of the filament should have younger, bluer galaxies, and the whole structure should be embedded in a vast halo of dark matter, invisible but gravitationally dominant. Simulations also make predictions about the future. As the universe continues to expand and dark energy's influence grows, the growth of structure will slow and eventually stop. Distant structures will recede beyond our cosmic horizon. The cosmic web will become more fragmented, more isolated, as expansion overcomes gravity on ever larger scales. Billions of years from now, the cosmic web will look different than it does today. Clusters will still exist, held together by their own gravity, but the filaments connecting them will thin and eventually break. Each cluster will become an island, isolated from its neighbors, surrounded by an ever-expanding void. But that's far in the future. For now, simulations help us understand the universe as it is, and how it came to be this way. They're essential tools for modern cosmology, allowing us to test our theories, explore scenarios we can't observe directly, and make predictions about what future observations should reveal. The agreement between simulations and observations, between the virtual universes we create in computers and the real universe we observe through telescopes, is one of the great successes of modern science. It tells us that we've figured out something fundamental about how the cosmos works. Let's take a journey through time, from the very beginning of the universe to the present day, watching as structure emerges from near-perfect smoothness. This is the story of how the cosmic web came to be, how tiny quantum fluctuations in the infant universe grew over 13.8 billion years into structures spanning billions of light years. In the beginning, there was the Big Bang, not an explosion in space, but an explosion of space itself. The universe began in an extremely hot, dense state, expanding rapidly, cooling as it expanded. But we need to go back even further, to the first fraction of a second, to understand where the seeds of structure came from. In the first 10 circumflex 35 seconds after the Big Bang, the universe underwent a period called cosmic inflation. Space expanded exponentially fast, doubling in size every 10 circumflex 37 seconds or so. This sounds absurdly fast, and it is. During inflation, the universe grew from smaller than an atom to perhaps the size of a grapefruit in a tiny fraction of a second. Inflation was driven by a hypothetical field, the inflaton field, which had energy even in empty space. This energy drove the expansion, pushing space apart faster than light could travel through it. Then, when inflation ended, the energy in the inflation field converted into ordinary matter and radiation, reheating the universe. But here's the crucial part. Quantum mechanics tells us that even empty space has fluctuations, tiny random variations in energy that appear and disappear on microscopic scales. During inflation, these quantum fluctuations were stretched to enormous sizes. What began as quantum jitter smaller than an atom was inflated to scales larger than galaxies. These stretched quantum fluctuations became the density variations that would eventually grow into the cosmic web. Some regions ended up slightly denser than average, others slightly less dense, with the pattern frozen into space as inflation ended. The amplitude of these fluctuations was incredibly small, about 1 part in 100,000. If you measured the density in different regions of the universe shortly after inflation, you'd find most regions had almost exactly the same density, varying by only 0.001%. But that tiny variation was enough. After inflation ended, the universe continued expanding, but at a more sedate rate. The temperature dropped, the energy density decreased, and matter began to behave according to more familiar physics. For the first 380,000 years, the universe was opaque. It was filled with hot plasma, a soup of electrons and atomic nuclei where photons couldn't travel freely. They were constantly being absorbed and re-emitted by the charged particles. If you had eyes and could somehow exist in this environment, you wouldn't be able to see anything more than a few meters away. Everything would be glowing, uniformly bright in all directions. During this time, the density variations created by inflation were present, but couldn't grow much. Ordinary matter was tightly coupled to radiation through constant interactions, and radiation pressure resisted gravitational collapse. The fluctuations persisted, but didn't amplify significantly. Dark matter, however, wasn't coupled to radiation. It could begin collapsing under gravity immediately. Small dark matter halos started forming, growing slowly, pulling in more dark matter from their surroundings. Then, 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons combined with nuclei, creating neutral hydrogen and helium atoms. With the charged particles gone, photons could suddenly travel freely. The universe became transparent. This moment is called recombination, and the light released at this moment is what we detect today as the cosmic microwave background. Those photons have been traveling through space ever since, stretched by cosmic expansion from visible wavelengths to microwaves, but still carrying information about what the universe looked like at that early time. The tiny temperature variations we see in the CMB, about 1 part in 100,000, map the density variations that existed at recombination. Slightly denser regions appear slightly warmer, slightly less dense regions appear slightly cooler. This pattern, imprinted on the CMB, is the ancestor of all the structure we see today. After recombination, ordinary matter could finally start collapsing into the dark matter halos that had already formed. Gas fell into these gravitational wells, pulled by the gravity of the dark matter. As it fell, it heated up through compression, but it also cooled through radiation, emitting photons that carried energy away. Where the cooling was efficient enough, the gas could collapse to high densities, eventually becoming dense and hot enough to ignite nuclear fusion. The first stars were born, probably about 100 to 200 million years after the Big Bang. These first stars were very different from stars today. They formed from gas that had no heavy elements, only hydrogen and helium from the Big Bang. Without heavy elements, the gas couldn't cool as efficiently, which meant it had to collapse to larger masses before forming stars. The first stars were probably hundreds of times more massive than our Sun. Massive stars live fast and die young. They burn their fuel in only a few million years, then explode as supernovae. These explosions enriched the surrounding gas with the first heavy elements, carbon, oxygen, silicon, iron, forged in the star's cores and in the supernova explosions themselves. As hundreds of millions of years passed, more stars formed. Dark matter halos grew through mergers, small halos combining to form larger ones. Stars collected in these halos, forming the first galaxies, small irregular collections of stars much smaller than modern galaxies. By about 500 million to 1 billion years after the Big Bang, the first real galaxies had assembled. These early galaxies were actively forming stars, glowing brightly in ultraviolet light. Some of them contained supermassive black holes at their centers, though we don't fully understand how those black holes formed so early. The universe during this era looked very different than today. Galaxies were smaller, bluer, more irregular. The cosmic web was denser, with shorter distances between structures. The expansion of the universe hadn't yet separated things as much as it has now. As billions of years passed, the hierarchical growth of structure continued. Small galaxies merged to form larger ones. Dark matter halos continued to grow. Matter flowed along filaments from less dense regions toward denser ones. The cosmic web became more pronounced, with greater contrast between dense filaments and empty voids. By about 3 to 4 billion years after the Big Bang, the first massive galaxy clusters had formed. These were the nodes of the cosmic web, where multiple filaments intersected, creating concentrations of hundreds or thousands of galaxies bound together by gravity. the Hercules Corona Borealis Great Wall, if we're seeing it at a distance of 10 billion light-years, existed when the universe was only about 3.8 billion years old. It had already assembled by this early time, which is part of what makes it surprising. Structures this large should take a long time to form, longer than 3.8 billion years by most estimates. This timeline suggests either that the initial density fluctuations in that region were particularly large, giving structure a head start, or that our models of structure formation are missing something, underestimating how quickly large structures can assemble. Between 4 and 8 billion years after the Big Bang, the universe was in its prime era of structure formation. This was when most galaxy clusters reached their current masses. This was when most of the stars that exist today were formed. Star formation rates across the universe peaked during this era and have been declining ever since. Our own solar system formed about 9 billion years after the Big Bang, or about 4.6 billion years ago. By this time, the universe was already fairly mature. The cosmic web had largely reached its current configuration. The Milky Way had formed. The local group had assembled. Our corner of the universe looked much as it does today. Over the last several billion years, structure formation has continued, but at a slower pace. Dark energy, which began dominating the universe's expansion about 5 billion years ago, has been working against gravity, accelerating the expansion and making it harder for new structures to form. Galaxy clusters have continued to grow through mergers and accretion, but the rate of growth has slowed. Filaments have stretched as the universe expanded. Voids have grown larger and emptier. The cosmic web has become more tenuous, more spidery, more fragmented, and this process will continue into the future. As dark energy drives faster and faster expansion, structure growth will slow further and eventually stop. The cosmic web will freeze in its final configuration, then gradually become more isolated as distant structures recede beyond our cosmic horizon. But for now, 13.8 billion years after the Big Bang, we live in an era where structure still exists, where the cosmic web spans the observable universe, where structures like the Hercules Corona Borealis Great Wall connect thousands of galaxies across billions of light-years. This entire timeline, from quantum fluctuations in the first instant of inflation to the largest structures we observe today, represents the amplification of tiny variations through gravity over cosmic time. What began as 1 part in 100,000 variations in density has grown into variations of factors of thousands or millions, from the near vacuum of voids to the dense cores of galaxy clusters. Gravity is patient. It works slowly but relentlessly, pulling matter toward matter, amplifying small differences into large ones. Given enough time, given 13.8 billion years, gravity transforms a nearly smooth universe into the rich, complex cosmic web we observe. And we're here to witness it, to map it, to understand it. We're the universe looking back at its own history, tracing the path from its beginning to the present, understanding how we came to exist in this particular place at this particular time. The Hercules Corona Borealis Great Wall is not alone in pushing the boundaries of how large cosmic structures can be. Several other massive structures have been discovered, each challenging our understanding in different ways. Let's explore these other contenders and see how they compare. The giant GRB ring was discovered in 2015 by Lajos Balázs and his colleagues, the same research group that found the Hercules Corona Borealis Great Wall. Like that structure, the giant GRB ring was detected through the distribution of gamma-ray bursts. What makes this structure particularly puzzling is its shape. It appears to be ring-shaped, roughly circular, about 5 billion light-years in diameter. That's half the size of the Hercules Corona Borealis Great Wall in linear extent, but the shape is what's truly unusual. The cosmic web naturally produces filaments and sheets and nodes, but it doesn't naturally produce rings. Rings aren't predicted by standard cosmological models. They're not an expected outcome of gravity acting on random density fluctuations. If the giant GRB ring is real, if it's truly a coherent ring-shaped structure rather than a chance alignment, then it suggests something unusual happened in that region of space. Several explanations have been proposed. Maybe it's not a ring at all, but a projection effect, a spherical shell of matter that happens to be oriented so we see it edge on, creating the appearance of a ring. Maybe it's the remnant of some extremely large-scale process in the early universe that we don't yet understand. Or maybe it's a statistical fluctuation, an apparent pattern that doesn't actually represent a physical structure. The statistical analysis showed significance at about the 5 sigma level, similar to the Hercules Corona Borealis Great Wall. But as with that structure, questions remain about whether the clustering truly represents a coherent object. The Boss Great Wall was discovered in 2016 using data from the Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey. This structure is more conventional in shape than the giant GRB ring. It's a filament, a wall-like concentration of galaxies stretching about 1 billion light-years across space. What makes the Boss Great Wall noteworthy is that it was detected through direct galaxy surveys rather than gamma-ray bursts. Astronomers mapped the positions of hundreds of thousands of galaxies and found this massive concentration. The detection is more robust than those based on gamma-ray bursts because it's based on mapping the galaxies themselves, the primary constituents of the cosmic web. The Boss Great Wall is located about 4.5 to 6.5 billion light-years from Earth. It's comparable in size to the Sloan Great Wall, perhaps slightly larger depending on exactly how you define its boundaries. It contains numerous galaxy clusters connected by filaments, forming a coherent structure that stands out clearly in maps of galaxy distribution. This structure doesn't challenge the cosmological principle in the same way the Hercules Corona Borealis Great Wall might, because it's smaller, well within the range that simulations predict. But it's still impressive, a billion light-year-long concentration of matter, and it provides valuable data for testing models of structure formation. The Laniakea supercluster is different from these other structures in a fundamental way. It's not defined by where galaxies are located, but by how they're moving. We'll discuss this in much more detail in the next section, but briefly, Laniakea is defined by gravitational flows. Galaxies aren't stationary. They're moving, partly due to cosmic expansion, but also due to peculiar velocities caused by gravity. Galaxies are falling toward massive concentrations of matter, creating large-scale flows through the cosmic web. Laniakea is the region of space containing all galaxies that are flowing toward the same gravitational basin. It's about 520 million light-years across and contains about 100,000 galaxies, including our own Milky Way. It's our cosmic home, the supercluster to which we belong. What makes Laniakea interesting is that it represents a different way of defining structures. Traditional definitions look at where matter is concentrated. Laniakea looks at where matter is flowing. This captures something real about the dynamics of the cosmic web, about how structures are connected not just spatially, but gravitationally. By this metric, Laniakea is substantial but not record-breaking. It's smaller than the Sloan Great Wall or the Boss Great Wall, and much smaller than the Hercules Corona Borealis Great Wall. But it's home, and that makes it special to us. The Shapley supercluster is one of the most massive structures in the nearby universe. It's located about 650 million light-years from Earth and contains more than 8,000 galaxies, with a total mass estimated at about 10 million billion times the mass of our Sun. The Shapley supercluster is dense, extremely dense by cosmic standards. It's one of the dominant mass concentrations in our region of space, and its gravity affects the motions of galaxies across hundreds of millions of light-years. In fact, our local group is being pulled toward the Shapley supercluster, though we'll never actually reach it, because cosmic expansion will carry it beyond our reach first. What makes Shapley noteworthy isn't its size. It's only about 350 million light-years across, but its density and mass. It's one of the most massive structures known, and it plays an important role in the large-scale dynamics of the cosmic web in our region of the universe. The Saraswati supercluster, discovered in 2017, is another massive structure, about 652 million light-years across and located about 4 billion light-years from Earth. It contains about 400 galaxies organized into 43 separate clusters, all connected by filaments. The mass of Saraswati is estimated at about 20 million billion solar masses, comparable to Shapley. What makes it particularly interesting is its distance. At 4 billion light-years, we're seeing Saraswati as it was when the universe was only about 10 billion years old. The fact that such a massive organized structure had already formed by that time provides constraints on models of structure formation. How does the Hercules Corona Borealis Great Wall compare to all of these? In terms of size, if the Hercules Corona Borealis Great Wall is truly 10 billion light-years across, it dwarfs everything else. The Boss Great Wall at 1 billion light-years is 1/10 its size. The Saraswati supercluster at 652 million light-years is about 1/15 its size. Even the giant GRB ring at 5 billion light-years in diameter is only half as large. But there's an important caveat. The Hercules Corona Borealis Great Wall's size is uncertain because it was detected through gamma-ray bursts rather than direct galaxy mapping. The other structures I've mentioned, with the exception of the giant GRB ring, were detected through galaxy surveys, which are more reliable. In terms of mass, we don't have good estimates for the Hercules Corona Borealis Great Wall, because we don't know exactly how many galaxies it contains, or how they're distributed. The structures that have been mapped through galaxy surveys have better mass estimates. The Shapley and Saraswati superclusters, for instance, contain tens of millions of billions of solar masses. If the Hercules Corona Borealis Great Wall is real and truly 10 billion light-years long, it would have to contain far more mass than these structures, perhaps hundreds of millions of billions of solar masses or more. But we can't confirm this without detailed observations. In terms of how well established these structures are, there's a spectrum. The Boss Great Wall and Sloan Great Wall are well confirmed through multiple independent observations. Laniakea is well established because it's based on mapping peculiar velocities, a robust technique. Shapley and Saraswati are confirmed superclusters with measured properties. The Hercules Corona Borealis Great Wall and the giant GRB ring are less certain. They're based on gamma-ray burst distributions, which is a less direct probe of structure. Follow-up observations have been inconclusive. They might be real, or they might be artifacts or chance alignments. The jury is still out. This is how science works. Multiple groups make observations, analyze data, announce discoveries. Then other groups follow up, trying to confirm or refute. Over time, consensus emerges about what's real and what's not. Some discoveries hold up to scrutiny and become accepted parts of our understanding of the universe. Others don't withstand follow-up observations and are recognized as errors or misinterpretations. Still others, like the Hercules Corona Borealis Great Wall, remain in limbo, not fully confirmed but not definitively refuted either. What's clear is that the universe contains structures at scales approaching billions of light-years. Whether the specific largest structure is the Hercules Corona Borealis Great Wall at 10 billion light-years, or the Boss Great Wall at 1 billion light-years, or something else we haven't discovered yet, structures at these enormous scales exist, and they challenge our understanding of how the universe is organized. Each of these structures, confirmed or tentative, tells us something about the cosmic web. They map out the largest scale organization of matter in the observable universe. They show us where gravity has been most effective at collecting matter over cosmic time. They reveal the fingerprints of the initial conditions in the early universe, the density fluctuations that seeded all later structure. And they remind us that the universe is vast, complex, and still full of mysteries waiting to be unraveled. let me tell you about where we live in the cosmic web. Not just our solar system or our galaxy, but our place in the largest scale structure that contains us. This is Laniakea, and understanding it requires thinking about the universe in a different way. For most of history, when astronomers talked about superclusters, they were talking about regions where galaxies are concentrated. The Virgo supercluster, for instance, which was thought to be our home supercluster for decades, was defined as the region containing the Virgo cluster and all the nearby galaxy groups, including our own local group. But in 2014, Brent Tully and his colleagues proposed a different way of defining superclusters. Instead of looking at where galaxies are, they looked at where galaxies are going. They mapped the peculiar velocities of galaxies, the motions caused by gravity rather than cosmic expansion, and used these to define basins of attraction, regions of space where all galaxies are flowing toward the same gravitational center. This revealed something remarkable. The Virgo supercluster, as traditionally defined, wasn't a coherent structure at all. It was just one part of a much larger system. The galaxies, in what we called the Virgo supercluster, weren't all flowing toward the Virgo cluster. Some were, but others were flowing in different directions, toward a much more massive concentration called the Great Attractor. The Great Attractor is a gravitational anomaly located about 250 million light-years away in the direction of the constellations Centaurus and Hydra. It was discovered in the 1970s and 1980s, when astronomers noticed that our local group and many other nearby galaxies are all moving toward this region of space at hundreds of miles per second. For years, the Great Attractor was mysterious because it lies behind the plane of the Milky Way, in a region obscured by dust and gas from our own galaxy. We could measure its gravitational effects, but we couldn't see what was causing them. Eventually, observations using infrared light and radio waves, which can penetrate the dust, revealed that the Great Attractor region contains a massive concentration of galaxy clusters. It's one of the densest regions in our corner of the universe, and its gravity dominates the motions of galaxies across hundreds of millions of light-years. But even the Great Attractor turned out to be part of something larger. When Tully and his team mapped peculiar velocities across a large volume of space, they found that the region flowing toward a common gravitational basin extends about 520 million light-years across. They named this structure Laniakea, from Hawaiian words meaning immeasurable heaven or immense heaven. It's the gravitational drainage basin containing our galaxy, the region of the cosmic web where all matter is flowing inward toward a common center. Laniakea contains about 100,000 galaxies with a total mass of about 100 million billion times the mass of our Sun. That's roughly 100 quadrillion solar masses, an almost incomprehensible amount of matter spread across 520 million light-years. The structure isn't uniform. It has denser regions and less dense regions, filaments and voids, just like the cosmic web as a whole. But what unifies it is motion. Every galaxy in Laniakea is, on average, moving inward toward the denser regions. Our Milky Way is located in one of the outer regions of Laniakea, flowing along with the local group toward the Virgo cluster and ultimately toward the Great Attractor region. We're moving at about 600 kilometers per second relative to the cosmic microwave background, and much of that motion is caused by the gravitational pull of the mass concentrations within Laniakea. The boundary of Laniakea isn't sharp. It's defined by the watershed between different gravitational basins. Imagine rain falling on a mountain range. Water on one side of the ridge flows into one valley. Water on the other side flows into a different valley. The ridge is the watershed, the boundary between drainage basins. Laniakea's boundaries are similar. They're the regions where the gravitational flows change direction, where galaxies stop flowing toward our gravitational basin and start flowing toward neighboring basins. Beyond Laniakea's boundaries lie other superclusters defined by their own gravitational flows. The Shapley supercluster, which I mentioned earlier, is one of these neighboring structures. It's located beyond Laniakea's boundary, and galaxies there are flowing toward Shapley's center rather than toward ours. But Shapley's gravity is so strong that it affects even galaxies within Laniakea, creating an additional pull beyond our own supercluster's internal flows. This nested structure, basins within basins, flows within flows, is characteristic of the cosmic web. Structure exists at multiple scales, and each scale has its own dynamics, its own patterns of motion. What makes the Laniakea definition of superclusters valuable is that it captures something physically meaningful. Traditional definitions based on galaxy density are somewhat arbitrary. Where exactly do you draw the boundary between one supercluster and another? There's no obvious answer because the cosmic web is continuous, with no clear breaks. But the flow-based definition has a natural boundary. It's where the flow changes direction. This makes Laniakea a more physically motivated structure than the old Virgo supercluster definition. However, there's an important caveat. Laniakea is not a gravitationally bound structure in the way galaxy clusters are. The galaxies within Laniakea are not orbiting a common center. They're flowing inward due to gravity. But cosmic expansion is working against this flow. In regions far from the center of Laniakea, expansion wins. Those galaxies will never actually reach the center. They're flowing inward relative to the cosmic expansion, but the expansion is strong enough that the distance between them and the center is still increasing over time. Only in the densest central regions, where gravity is strongest, will structures continue to collapse and merge. The Virgo cluster, the Great Attractor region. These will continue to grow. But the outer reaches of Laniakea will gradually be carried away by expansion. In the far future, as dark energy drives faster and faster expansion, Laniakea will fragment. The connections between different parts will break. Each major concentration will become isolated, surrounded by expanding voids, unable to interact with its former neighbors. But that's billions of years away. For now, Laniakea is a coherent structure defined by gravitational flows, and we're part of it. Understanding Laniakea helps us understand our place in the cosmic web. The Milky Way isn't just a random galaxy floating in space. We're part of the local group, which is part of Laniakea, which is part of the larger cosmic web stretching across the observable universe. We're connected to structures hundreds of millions of light-years away through gravity. The mass in the Great Attractor region, the mass in the Shapley supercluster. These affect our motion through space. We're not isolated. We're part of a vast, interconnected network. This perspective, understanding the flows and connections that define our cosmic neighborhood, is one of the great achievements of modern cosmology. For most of human history, we didn't even know other galaxies existed. 100 years ago, we thought the Milky Way was the entire universe. Now we know we're in a galaxy, part of a group, part of a supercluster, part of the cosmic web. Each scale reveals new structure, new organization, new patterns. And each scale helps us understand the universe a little better. Laniakea is home, in a cosmic sense. It's the largest structure to which we truly belong, defined by the gravitational flows that connect us to our neighbors across hundreds of millions of light-years. Smaller than the Hercules Corona Borealis Great Wall, but in many ways more meaningful because it's ours. Because we're part of it, moving through it, connected to it through the invisible threads of gravity that shape the cosmic web. How do we know how far away something is? For nearby objects, this is simple. You can measure parallax, the apparent shift in position as you view something from different locations. Hold your finger at arm's length and alternately close each eye. Your finger appears to shift position relative to the background. That shift is parallax, and by measuring it, you can calculate the distance to your finger. Astronomers use the same principle for nearby stars. As Earth orbits the Sun, our viewing position changes. Stars appear to shift position slightly relative to more distant stars. By measuring this shift and knowing the diameter of Earth's orbit, We can calculate the distance to the star through basic trigonometry. This works well for stars within a few hundred light-years of Earth. Beyond that, the parallax becomes too small to measure accurately, even with our best telescopes. We need other methods. This is where the cosmic distance ladder comes in. It's not an actual ladder, but a series of measurement techniques, each one calibrated using the previous one, each extending our reach a little farther into the universe. The second rung of the ladder uses variable stars, particularly Cepheid variables. These are stars that pulsate, growing brighter and dimmer in a regular cycle. The period of pulsation, the time from one maximum brightness to the next, is related to the star's intrinsic luminosity, how bright it actually is. Henrietta Swan Leavitt discovered this relationship in 1908 by studying Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. She noticed that Cepheids with longer periods were intrinsically brighter than those with shorter periods. The relationship was tight and predictable. This is incredibly useful. If you measure a Cepheid's period, you know its intrinsic luminosity. If you measure its apparent brightness as seen from Earth, you can calculate its distance. The relationship between intrinsic luminosity, apparent brightness, and distance is straightforward. The farther away something is, the dimmer it appears, following an inverse square law. Cepheids are bright enough to be seen in nearby galaxies, out to distances of about 100 million light-years with current telescopes. This allowed astronomers to measure distances to galaxies in our cosmic neighborhood and begin mapping the local universe. But Cepheids have limits. Beyond about 100 million light-years, even the brightest Cepheids become too faint to detect reliably. We need something even brighter. Enter Type Ia supernovae. These are thermonuclear explosions of white dwarf stars that have accumulated too much mass from a companion star. When a white dwarf exceeds a critical mass, about 1.4 times the mass of our Sun, it can no longer support itself and collapses, triggering a runaway nuclear fusion reaction that destroys the entire star in a spectacular explosion. What makes Type Ia supernovae valuable for distance measurements is that they all reach approximately the same peak brightness. Because they're triggered by exceeding a specific mass threshold, they all explode under similar conditions, producing similar amounts of light. This makes them standard candles, objects with known intrinsic brightness. If you observe a Type Ia supernova, measure its peak apparent brightness, and know its intrinsic brightness, you can calculate its distance, just as with Cepheids. Type Ia supernovae are extraordinarily bright, briefly outshining entire galaxies. They can be seen across billions of light-years, extending our distance measurements far beyond what's possible with Cepheids. There's a subtlety here. Not all Type Ia supernovae have exactly the same intrinsic brightness. There's some variation, but astronomers discovered that the variation is correlated with how quickly the supernova brightens and fades. Brighter supernovae take longer to fade. By measuring the light curve, the plot of brightness versus time, you can determine exactly how intrinsically bright that particular supernova was, making the distance calculation more accurate. Using Type Ia supernovae, astronomers can measure distances out to about 10 billion light-years or more, covering a substantial fraction of the observable universe. This is how we map the large-scale structure of the cosmos, how we determine that structures like the Hercules Corona Borealis Great Wall are 10 billion light-years away. But even Type Ia supernovae have limitations. They're rare events. In a typical galaxy, a Type Ia supernova occurs perhaps once every few hundred years. You might wait decades or centuries for a supernova to occur in a particular galaxy you're interested in, and the supernova is only visible for a few weeks or months before fading below detectability. This is why large surveys are important. If you monitor millions of galaxies, you'll catch supernovae occurring in some of them. The Supernova Legacy Survey, the Sloan Digital Sky Survey Supernova Survey, and other programs have discovered thousands of Type Ia supernovae and used them to map cosmic structure and measure the expansion history of the universe. For the most distant objects, even type E supernovae aren't bright enough. At distances beyond about 10 billion light-years, we rely primarily on redshift as a distance indicator rather than standard candles. Redshift measures how much light from an object has been stretched by the expansion of space during its journey to us. The farther away an object is, the more time the light has spent traveling, the more the universe has expanded during that time, and the larger the redshift. The relationship between redshift and distance isn't perfectly linear, because it depends on the expansion history of the universe, which is affected by the amounts of matter and dark energy. But cosmologists can calculate this relationship precisely using our understanding of cosmology. By measuring the redshift of a galaxy or other object, we can determine its distance with good accuracy, even for objects at the edge of the observable universe. This is the primary method used for mapping large-scale structure at the greatest distances. The cosmic distance ladder, from parallax to Cepheids to type 1a supernovae to redshift, allows us to measure distances across the entire observable universe. Each rung is calibrated using the previous one, so errors can accumulate. If our calibration of Cepheids is slightly off, that error propagates to our calibration of type 1a supernovae, which propagates to our understanding of the expansion history, which affects our redshift to distance conversion. This is why astronomers continually work to improve calibrations, using multiple methods to cross-check results, reducing uncertainties. The Hubble Space Telescope has been particularly valuable for this, observing Cepheids in distant galaxies with precision impossible from ground-based telescopes. Future missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will extend these measurements even further, potentially finding new standard candles or improving calibrations of existing ones. For structures like the Hercules Corona Borealis Great Wall, the distance determination relies on measuring redshifts of gamma-ray bursts. The bursts themselves are detected by satellites. Follow-up observations with ground-based telescopes measure the spectra of the afterglows, identifying emission and absorption lines whose wavelengths have been redshifted. From the amount of redshift, the distance is calculated using cosmological models. The uncertainty in this distance depends on the precision of the redshift measurement and on how well we understand the expansion history of the universe. But for objects at these distances, the typical uncertainty is a few percent, which translates to a few 100 million light-years. This means when we say the Hercules Corona Borealis Great Wall is 10 billion light-years away, there's an uncertainty of perhaps a few 100 million light-years in that number. The structure might be 9.7 billion light-years away or 10.3 billion light-years away. Given the scale we're talking about, this is actually quite precise. Understanding how we measure cosmic distances helps us appreciate the challenge of mapping the universe. It's not like mapping Earth where you can directly measure distances with GPS or surveying equipment. We're measuring distances to objects billions of light-years away using indirect methods, calibrating one method against another, building up a chain of measurements that extends from our solar system to the edge of the observable universe. And remarkably, it works. The distances we measure are consistent across different methods. The cosmic distance ladder is robust, and that allows us to create three-dimensional maps of the universe, revealing the cosmic web, discovering massive structures, understanding our place in the cosmos. Redshift is one of the most important concepts in modern cosmology. It's how we know the universe is expanding. It's how we measure distances to the most remote objects. It's how we probe the history of the cosmos. Understanding redshift means understanding the dynamic nature of the universe itself. Let's start with the basic physics. Light is a wave, and like all waves, it has a wavelength, the distance from one wave crest to the next. Different wavelengths correspond to different colors. Red light has a longer wavelength than blue light. Infrared has an even longer wavelength. Ultraviolet has a shorter wavelength. When a source of light is moving away from you, the wavelength of the light you receive is stretched, shifted toward longer wavelengths, toward the red end of the spectrum. When a source is moving toward you, the wavelength is compressed, shifted toward shorter wavelengths, toward the blue end of the spectrum. This is called the Doppler effect, and you've experienced it with sound. When an ambulance approaches with its siren wailing, the pitch sounds higher than when it's moving away. The sound waves are compressed as the ambulance approaches, raising the frequency and pitch. They're stretched as it recedes, lowering the frequency and pitch. Light works the same way. If a star is moving away from us, its light is red-shifted. If it's moving toward us, its light is blue-shifted. By measuring the shift, we can calculate the velocity of motion along our line of sight. This is straightforward for objects moving through space. But in cosmology, there's an additional effect. The universe itself is expanding. Space is stretching, carrying galaxies along with it. Light traveling through this expanding space gets stretched as well. This cosmological redshift is different from the Doppler effect in a subtle but important way. In the Doppler effect, objects are moving through space. In cosmological redshift, space itself is expanding, and the expansion stretches the light's wavelength as it travels. For nearby galaxies, the difference between these two effects is negligible. Both produce redshift, and both give similar results. But for very distant galaxies, cosmological redshift dominates, and the relationship between redshift and velocity becomes more complex. Here's how we measure redshift in practice. We observe a galaxy or other object and collect its light using a telescope. We spread that light into a spectrum, showing the intensity at different wavelengths. Within that spectrum, we look for features, emission or absorption lines produced by specific elements. Hydrogen, for instance, produces a series of absorption lines at specific wavelengths. In a laboratory on Earth, we know exactly where those lines should appear. But when we observe a distant galaxy, those lines appear at longer wavelengths than expected. They've been shifted toward the red. By measuring how much the lines have shifted, we calculate the redshift, usually denoted by the letter Z. If a line that should appear at 500 nanometers appears instead at 600 nanometers, the redshift is Z equals 600,500/500 equals 0.2. For small redshifts, the relationship between redshift and velocity is approximately v equals zz, where c is the speed of light. So, a redshift of 0.2 corresponds to a velocity of about 20% the speed of light, or about 37,000 miles per second. For large redshifts, the relationship becomes more complex because we have to account for relativistic effects and the changing expansion rate of the universe over cosmic time. But the principle is the same. Larger redshift means greater distance and higher recession velocity. The Hercules Corona Borealis Great Wall has components with redshifts around z equals 2 or higher. This means the light we're seeing has been stretched to about 3 times its original wavelength by cosmic expansion. Light that was emitted as ultraviolet has been stretched into the visible range. Light emitted as visible has been stretched into the infrared. This large redshift tells us 2 things. First, the structure is very far away, about 10 billion light-years. Second, we're seeing it as it was about 10 billion years ago, when the universe was only about 3.8 billion years old, less than a third of its current age. Distance and look-back time are intimately connected. The farther away something is, the longer light has taken to reach us, and the farther back in time we're seeing. When we observe distant objects, we're not seeing the universe as it is today. We're seeing cosmic history. This creates an interesting situation for structures like the Hercules Corona Borealis Great Wall. Different parts of the structure are at different distances from us, which means we're seeing them at different times in cosmic history. The nearest edge might be at a redshift of z equals 1.9, corresponding to a look-back time of about 9.5 billion years. The farthest edge might be at z equals 2.1, corresponding to a look-back time of about 10.5 billion years. That's a difference of a billion years. We're not seeing the structure as it was at a single moment. We're seeing it smeared across a billion years of cosmic time. The far edge shows us what that part of the structure looked like a billion years before we see the near edge. This complicates analysis. When we try to understand the structure's properties, its size, its mass distribution, we have to account for this time smearing. The structure has been evolving during that billion-year span. Galaxies have been forming, merging, moving. The gas distribution has changed. Matter has flowed along filaments toward clusters. Redshift also tells us about cosmic expansion itself. In the 1920s, Edwin Hubble made the observation that revolutionized cosmology. He measured distances to nearby galaxies using Cepheid variables and measured their redshifts spectroscopically. When he plotted distance versus redshift, he found a linear relationship. More distant galaxies had larger redshifts. This was evidence that the universe is expanding. Every galaxy is receding from every other galaxy, not because they're all moving away from us specifically, but because space itself is expanding, carrying galaxies along with it. The slope of Hubble's relationship, the ratio of recession velocity to distance, is called the Hubble constant, denoted h0. Its current value is approximately 70 kilometers per second per megaparsec, though there's some debate about the exact number. This means for every megaparsec, about 3.26 million light-years of distance, recession velocity increases by about 70 kilometers per second. At 10 billion light-years, the recession velocity is enormous, approaching the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Rather, space itself is expanding, and the cumulative expansion across billions of light-years adds up to an effective recession velocity exceeding light speed. This is why the observable universe is larger than you might expect given its age. The universe is 13.8 billion years old, so you might think we can only see objects whose light has been traveling for 13.8 billion years, corresponding to a distance of 13.8 billion light-years. But space has been expanding while the light was traveling. Objects whose light has been traveling for 13.8 billion years are now much farther away than 13.8 billion light-years, roughly 46.5 billion light-years, due to the expansion during the light's journey. Redshift measurements have revealed the expansion history of the universe. By measuring redshifts and distances to Type Ia supernovae at various distances, astronomers have mapped how the expansion rate has changed over time. What they found in 1998 shocked the cosmology community. The expansion is accelerating. Distant supernovae were dimmer than expected, indicating they were farther away than expected for their redshift. This could only be explained if the expansion of the universe has been speeding up over the last several billion years. This acceleration is driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy density. Dark energy has a repulsive gravitational effect, pushing space apart, driving faster expansion. This discovery earned the 2011 Nobel Prize in Physics, and it dramatically changed our understanding of the universe's future. Instead of eventually slowing and perhaps recollapsing, the universe will continue expanding faster and faster forever, becoming increasingly cold, dark, and empty over unimaginable timescales. For structures like the Hercules Corona Borealis Great Wall, dark energy's influence is important. It limits how much structure can grow. In the past, before dark energy dominated, gravity was winning its battle against expansion, and structure grew rapidly. Now, with dark energy dominant, expansion is winning, and structure growth has slowed. This is why finding structures as large as the Hercules Corona Borealis Great Wall at high redshift is surprising. The structure had to form early, during the era when gravity was still dominant, before dark energy took over. This puts constraints on how quickly structure can form, how strong the initial density fluctuations must have been, how dark matter behaves at large scales. Redshift is also used to map the three-dimensional structure of the universe. Galaxy surveys measure the positions of millions of galaxies on the sky, 2 coordinates. Then they measure redshifts, which provide the third coordinate, distance. Combining these creates a three-dimensional map showing how galaxies are distributed through space. These redshift surveys have revealed the cosmic web in stunning detail, showing filaments, voids, clusters, walls. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and upcoming surveys like those from the Vera Rubin Observatory are all based on measuring redshifts for vast numbers of galaxies. For the Hercules Corona Borealis Great Wall, redshift measurements of gamma-ray bursts revealed its existence. By plotting the positions and redshifts of hundreds of bursts, astronomers found a clustering that suggested a massive structure. Follow-up galaxy surveys in the same region are attempting to confirm this by mapping galaxies directly, using redshift to place them in three-dimensional space. Redshift is also our window into the early universe. The most distant galaxies we can observe have redshifts of Z equals 10 or higher. We're seeing them as they were when the universe was only a few 100 million years old. The James Webb Space Telescope is pushing this even further, finding galaxies at Z equals 13 or 14, seeing the universe when it was less than 300 million years old. At these extreme redshifts, galaxies look very different from modern galaxies. They're smaller, more irregular, more actively forming stars. By studying how galaxy properties change with redshift, we're studying cosmic evolution, watching galaxies grow and change over billions of years. Understanding redshift means understanding that we're not just looking out into space, but back into time. The universe has a history, and that history is written in the light that's been traveling toward us across cosmic ages. Every photon is a messenger carrying information about when and where it was emitted, about the state of the universe at that time, about the structures that existed and the processes that were occurring. The redshift of the Hercules Corona Borealis Great Wall tells us it's ancient, formed when the universe was young. It's a window into an earlier epoch of cosmic history, a time when the cosmic web was still taking shape, when dark energy hadn't yet begun to dominate, when structure could grow more freely than it can today. What is the Hercules Corona Borealis Great Wall actually made of? When we talk about a structure 10 billion light-years long, what physical components are we describing? Let's break down the composition of this massive filament and understand what it contains. First and foremost, the Hercules Corona Borealis Great Wall is made of galaxies. Thousands of galaxies, possibly tens of thousands, each one a collection of hundreds of billions of stars. Each star a massive ball of fusing hydrogen, creating light and heat through nuclear reactions. If the structure is real and truly 10 billion light-years long, and if it has a galaxy density typical of cosmic filaments, it might contain 10,000 to 100,000 galaxies or more. The exact number is uncertain because we haven't mapped all the galaxies in this region yet. The discovery was made through gamma-ray bursts, not direct galaxy counts. Each of these galaxies is separated from its neighbors by millions of light-years on average. Even in a filament, space is mostly empty. If you were somehow placed randomly within the Hercules Corona Borealis Great Wall, you'd most likely find yourself in near-perfect vacuum, with the nearest galaxy millions of light-years away, appearing as a faint smudge against the darkness. The galaxies within the structure aren't all the same. Some are massive spiral galaxies like our Milky Way, with beautiful spiral arms where stars are actively forming. Others are elliptical galaxies, older, redder, with less active star formation, shaped like footballs or spheres rather than disks. Still others are irregular galaxies, smaller, lacking clear structure, chaotic collections of stars and gas. At a redshift of Z, approximately equal to 2, we're seeing these galaxies as they were 10 billion years ago. Galaxies at that epoch looked different than galaxies today. Star formation rates were higher. Galaxies were generally smaller, not yet having grown to their current sizes through subsequent mergers. Many were more irregular, not yet having settled into the stable spiral or elliptical forms we see in the local universe. Within each galaxy, there are stars, hundreds of billions of stars per galaxy. If the structure contains 50,000 galaxies, and each galaxy contains an average of 200 billion stars, that's 10 quadrillion stars total. Each star is a nuclear furnace converting hydrogen into helium through fusion, releasing energy that powers the star's light. Most stars are small, red dwarfs burning slowly, living for trillions of years. Some are medium-sized yellow stars like our Sun. A few are massive blue giants burning bright and hot, living only millions of years before exploding as supernovae. Around many of these stars orbit planets. We know from observations in our own galaxy that most stars have planets. If the same is true at earlier cosmic epochs, which seems likely, then the number of planets in the Hercules Corona Borealis Great Wall might exceed the number of stars. Tens of quadrillions of worlds, most of which we'll never observe, never visit, never know anything about. Some of those worlds might harbor life. We don't know how common life is in the universe, but given the vast numbers involved, it seems likely that somewhere among those quadrillions of planets, life has emerged. Perhaps in many places. Perhaps intelligent life, civilizations, beings looking up at their own skies and wondering about the universe just as we do. But stars and planets and potential life are only part of the story. The galaxies are embedded in vast halos of dark matter. Remember, dark matter makes up about 85% of all matter in the universe. For every kilogram of ordinary matter, stars, gas, planets, there's about 5.7 kilograms of dark matter. The dark matter forms the gravitational scaffolding of the Hercules Corona Borealis Great Wall. It's the dark matter filaments that connect the galaxies, that channel matter along the structure, that provide the gravity needed to hold everything together against cosmic expansion. If you could somehow see dark matter, the Hercules Corona Borealis Great Wall would look much more substantial. Instead of isolated galaxies separated by emptiness, you'd see a continuous thread of dark matter stretching 10 billion light-years, with the galaxies embedded within it, like beads on a string. The total dark matter mass in the structure, if it's real, might be hundreds of quadrillions of solar masses. That's hundreds of quadrillions of times the mass of our Sun, almost all of it invisible, detectable only through its gravitational effects. Between the galaxies, filling the space along the filament, there's gas, mostly hydrogen and helium, left over from the Big Bang, plus small amounts of heavier elements produced by stars and scattered by supernovae and galactic winds. This intergalactic gas is extremely diffuse, typically only a few atoms per cubic meter, far thinner than any vacuum we can create in laboratories on Earth. But spread across billions of light-years, the total mass of gas is enormous, comparable to or exceeding the mass in all the stars in all the galaxies combined. Some of this gas is cold, only a few thousand degrees, too cool to emit much light. Other gas is warm, around 100,000 degrees, emitting faint ultraviolet light. Still other gas, particularly in the densest regions near galaxy clusters, is hot, millions of degrees, heated by gravitational compression and collisions, emitting X-rays. The hot gas is particularly important because it's visible to X-ray telescopes. By mapping X-ray emission, astronomers can trace the structure of filaments and clusters, seeing the warm/hot intergalactic medium that fills the cosmic web. For the Hercules Corona Borealis Great Wall, if follow-up X-ray observations detected a continuous thread of hot gas stretching across the structure, that would be strong evidence that it's a coherent filament, rather than separate structures that happen to align. The gas in cosmic filaments is also important because it's fuel for future star formation. As gas flows along filaments toward galaxy clusters, some of it cools and condenses, forming new stars in existing galaxies or even forming new small galaxies. The cosmic web is not static. It's a dynamic system where matter continuously flows, cools, heats, and gets recycled through stars. There's also dust mixed with the gas, tiny particles of silicates, carbon compounds, and other materials created in stars and expelled into space by stellar winds and supernova. The amount of dust is small compared to gas, typically about 1% of the gas mass, but it's important because dust absorbs and scatters light, affecting what we see when we observe distant galaxies. And there's radiation filling the space between galaxies. The cosmic microwave background permeates all of space. Photons left over from the Big Bang, cooled by cosmic expansion to just 2.7 degrees above absolute zero. Starlight from all the galaxies also contributes a faint glow of optical and ultraviolet photons filling intergalactic space. At earlier cosmic epochs, corresponding to the redshift where we're observing the Hercules Corona Borealis Great Wall, the cosmic microwave background was hotter than it is today, about 8 degrees above absolute zero at Z equals 2. Not hot by human standards, but measurably warmer than in the local universe. There are also high-energy particles, cosmic rays, protons, and heavier nuclei accelerated to nearly the speed of light by supernova explosions, black hole jets, and other violent processes. These cosmic rays travel through the cosmos, occasionally colliding with gas atoms, producing secondary particles and radiation. All of these components, galaxies, stars, planets, dark matter, gas, dust, radiation, cosmic rays, combine to form what we call the Hercules Corona Borealis Great Wall. It's not a single object, but a collection of components organized by gravity over billions of years into an elongated structure aligned along the cosmic web. The structure is dynamic, evolving. Stars are forming and dying. Galaxies are merging, gas is flowing, dark matter is redistributing itself in response to gravitational forces. What we see is a snapshot, a moment in a continuous process of evolution that's been ongoing for billions of years and will continue for billions more. If we could observe the Hercules Corona Borealis Great Wall, as it is today, 10 billion years after the light we're seeing left, it would look different. More mature galaxies, less active star formation, different arrangements of matter as structures have continued to grow and merge. But we can never see it as it is today. We can only see it as it was when the light began its journey. This is the nature of cosmic observation. We're seeing history frozen in the light that's been traveling toward us across billions of years. The Hercules Corona Borealis Great Wall, that exists now, assuming the structure is real, is forever hidden from us by the finite speed of light and the vast distances involved. But what we can see, the ancient light that's finally arriving at our telescopes, tells us something profound. It tells us that even when the universe was young, only 3.8 billion years old, gravity had already organized matter into structures spanning billions of light years. The cosmic web was already in place, the patterns already forming, the architecture already taking shape. Galaxy clusters are the cities of the cosmos, the most massive gravitationally bound structures in the universe. Within a structure like the Hercules Corona Borealis Great Wall, galaxy clusters are the densest nodes, the places where the filament is thickest, where the most matter has accumulated over cosmic time. A typical galaxy cluster contains hundreds to thousands of galaxies confined within a region about 10 to 15 million light-years across. That sounds large by human standards, and it is. But remember that galaxies in clusters are separated by millions of light-years from each other. Even in a cluster, space is mostly empty. What makes a cluster is that the galaxies are gravitationally bound. They're all orbiting a common center of mass, trapped by the combined gravitational pull of all the matter in the cluster. A galaxy in a cluster can't escape. It's stuck there for billions of years, continuously interacting gravitationally with its neighbors. These interactions have consequences. When galaxies pass close to each other, their gravitational fields distort each other's structures. Stars can be pulled out of one galaxy into tidal streams stretching across space. In extreme cases, galaxies can merge completely, combining into a single larger galaxy. In the densest central regions of clusters, mergers are common. Over billions of years, many smaller galaxies merge to form massive elliptical galaxies, often found at cluster centers. These central galaxies can contain trillions of stars, far more than the Milky Way's few hundred billion. But galaxies are just the visible component. The cluster is dominated by other forms of matter. About 85% of the matter in a galaxy cluster is dark matter. The dark matter forms an enormous halo, hundreds of millions of light-years across, much larger than the region where galaxies are concentrated. This dark matter halo is what creates the deep gravitational well that holds everything together. We know the dark matter is there because we can measure the velocities of galaxies in the cluster. They're moving at speeds of thousands of kilometers per second, far too fast to be held by the gravitational pull of the visible matter alone. Either the clusters are about to fly apart, which seems unlikely since they appear stable, or there's much more mass than we can see. The dark matter provides that additional mass. About 12 to 13% of the matter in a galaxy cluster is hot gas, the intra-cluster medium. This gas fills the space between galaxies, heated to temperatures of 10 to 100 million degrees by gravitational compression, as it fell into the cluster's potential well. When gas falls into a gravitational well, it speeds up, converting gravitational potential energy into kinetic energy, the energy of motion. For gas falling into a galaxy cluster, the velocities reach thousands of kilometers per second. When different streams of gas collide, as they must in the chaotic environment of a cluster, the kinetic energy converts into heat. The result is gas at tens of millions of degrees. Gas this hot emits X-rays, which is how we detect it. X-ray telescopes like Chandra and XMM Newton have mapped the intracluster medium in hundreds of clusters, revealing complex structures, shockwaves from cluster mergers, cavities carved by jets from supermassive black holes, temperature variations indicating different physical processes. The mass of hot gas in a typical cluster is actually larger than the mass of all the stars in all the galaxies combined. If you could somehow collect all the stars and weigh them, then collect all the gas and weigh it, the gas would outweigh the stars by a factor of about 6 to 1. This surprised astronomers when they first discovered it. We tend to think of galaxies as the main component of clusters because they're what we see, but they're actually a minor component by mass. Most of the ordinary matter is in the invisible hot gas filling the space between them. Only about 2% of the matter in a galaxy cluster is in stars and planets and everything else we think of as normal matter. The rest is dark matter and hot gas. We're truly living in a universe where the familiar is the exception, not the rule. Within the Hercules Corona Borealis Great Wall, if it's real, there should be dozens or hundreds of galaxy clusters. These would be the brightest, most massive concentrations along the filament, the nodes where multiple strands of the cosmic web intersect. Each cluster would contain its own population of galaxies, its own hot gas atmosphere, its own dark matter halo, and each would be at a slightly different stage of evolution. Some clusters might be young, still assembling, with galaxies falling in for the first time. The hot gas in such clusters would be relatively smooth, not yet disturbed by mergers. The galaxy population would be diverse, containing many spiral galaxies still forming stars. Other clusters might be old, mature, having assembled billions of years ago. Their hot gas would have reached equilibrium, settling into a smooth distribution, Their galaxy population would be dominated by elliptical galaxies, red and dead, having long ago consumed or lost their star-forming gas. Still other clusters might be in the process of merging. When two galaxy clusters collide, it's one of the most energetic events in the universe since the Big Bang. The collision takes hundreds of millions of years to complete, but the energy released is enormous. When clusters merge, their galaxies pass through each other like two swarms of bees interpenetrating. The distances between galaxies are so large that direct collisions are rare, but the hot gas doesn't pass through so easily. The gas from the two clusters collides, creating shockwaves that heat the gas to even higher temperatures, sometimes exceeding 100 million degrees. These shockwaves are visible in X-ray observations as bright arcs and edges in the gas distribution. They're signatures of violent collisions, regions where gas is being compressed and heated by supersonic flows. The dark matter from the two clusters also interacts, but differently. Dark matter is collisionless, meaning it doesn't crash into itself the way gas does. The dark matter halos pass through each other, their particles influencing each other only through gravity. This difference between how gas and dark matter behave during mergers has been observed directly in a few cases, most famously in the Bullet cluster. Observations show that the mass, mapped through gravitational lensing, is centered on the galaxies rather than on the gas. This is because the dark matter stayed with the galaxies during the collision, while the gas was stripped away and left behind. For the Hercules Corona Borealis Great Wall, observing the clusters within it in detail would tell us a lot about the structure's history. Are the clusters young or old? Are many of them merging, suggesting the structure is still actively assembling, or are they mostly mature, suggesting the structure formed long ago and has been relatively quiescent since? We don't have these detailed observations yet. The Hercules Corona Borealis Great Wall was discovered through gamma-ray bursts, which don't tell us much about cluster properties. Follow-up observations with X-ray telescopes could reveal the clusters, map their gas distributions, identify mergers, but such observations are challenging. X-ray telescopes have limited sensitivity and small fields of view. Mapping an entire 10 billion light-year structure in X-rays would require observing hundreds or thousands of different pointings, each taking hours or days of observation time. It's a massive undertaking that hasn't been done yet for this particular structure. Galaxy clusters also affect their member galaxies in dramatic ways. When a galaxy falls into a cluster, it encounters the hot intra-cluster medium. This gas is so hot and so diffuse that it doesn't seem like it would matter much. But for a galaxy moving at thousands of kilometers per second, the effect is significant. The galaxy experiences ram pressure, like the wind you feel when you stick your hand out of a moving car. The ram pressure from the intra-cluster medium can strip the star-forming gas out of the infalling galaxy, removing the fuel for future star formation. This process, called ram pressure stripping, transforms galaxies. A spiral galaxy rich in gas and actively forming stars falls into a cluster. The ram pressure strips its gas. Star formation shuts down. Over hundreds of millions of years, the galaxy fades from blue to red as its young hot blue stars die and aren't replaced. Eventually, it becomes a red, dead, elliptical galaxy, no longer forming stars, just aging quietly. This is why galaxy populations in clusters are different from those in the general field. Clusters have more elliptical galaxies and fewer spirals. They have more red galaxies and fewer blue ones. The cluster environment transforms galaxies, quenching their star formation, changing their properties. At the centers of most galaxy clusters sits a particularly massive galaxy, the brightest cluster galaxy, or BCG. These are among the largest galaxies in the universe, often containing trillions of stars, 10 times the mass of the Milky Way or more. BCGs form through a process called galactic cannibalism. As smaller galaxies fall toward the cluster center, they're eventually torn apart by tidal forces or merge directly with the central galaxy. Over billions of years, the central galaxy consumes dozens or hundreds of smaller galaxies, growing to enormous size. At the very center of the BCG, there's almost always a supermassive black hole, sometimes billions of times the mass of our Sun. This black hole is often active, accreting matter and launching powerful jets that carve enormous cavities in the surrounding hot gas. These jets, which we discussed earlier, play an important role in regulating the cluster. Without them, the hot gas would cool and fall toward the center, forming stars at a rate of hundreds of solar masses per year. But the jets inject energy into the gas, heating it back up, preventing this cooling catastrophe. This feedback between the central black hole and the cluster gas is a delicate balance that's been maintained for billions of years. It's one of the key processes shaping galaxy clusters and affecting how they evolve over time. Within the Hercules Corona Borealis Great Wall, each cluster tells part of the structure's story. Together, they map out where matter has accumulated most densely, where the gravitational field is strongest, where the cosmic web's architecture is most pronounced. Studying these clusters, understanding their properties, mapping their distributions, is essential to understanding the structure as a whole. The clusters are not just components of the wall. They are the wall, at least the visible, massive, dynamically important parts of it. For every region where matter has accumulated, there's a corresponding region where matter has been evacuated. These are the cosmic voids, vast empty regions that take up most of the volume of the universe. Understanding voids is just as important as understanding filaments and clusters for comprehending the cosmic web. Let me give you a sense of scale. A typical cosmic void might be 100 to 300 million light-years across. Within this enormous volume, there might be only a few dozen galaxies, sometimes fewer. The average density in a void is about 1/10 to 1/20th of the cosmic average. If the universe were perfectly uniform, you'd expect about 2,000 galaxies in a sphere, 300 million light-years across, based on typical galaxy densities. In a void, you might find only 100 galaxies. The rest of the matter has flowed out over billions of years, evacuating into the surrounding filaments and clusters. Voids are not completely empty. That would be impossible given that dark matter and dark energy fill all of space. But they're as close to empty as the universe gets. The few galaxies that do exist in voids are typically small, isolated dwarf galaxies that form from the sparse material that remained. These void galaxies are interesting in their own right. They evolve differently than galaxies in filaments or clusters because their environment is so different. They have almost no neighbors to interact with. They don't experience ram pressure stripping or tidal interactions. They evolve in relative isolation, quietly forming stars from their own gas supply over billions of years. Studies of void galaxies show they tend to be bluer and younger than average, still actively forming stars, less evolved than their counterparts in denser regions. This makes sense because they haven't been stripped of their gas by environmental effects, and they haven't merged with many neighbors to build up their mass. The shapes of voids are roughly spherical or ellipsoidal, carved out by the flow of matter toward the surrounding denser regions. Imagine water draining from a basin. The empty space left behind takes the shape of the basin, determined by where the water flowed out. Cosmic voids are similar. Over billions of years, matter has flowed out along the paths of steepest gravitational gradient, moving from less dense regions toward denser ones. The voids are what's left behind, the regions where matter used to be, but has since departed. The boundaries of voids are not sharp. There's no sudden transition from empty to full. Instead, there's a gradual increase in galaxy density as you move from the center of a void toward its edges. At the center, you might find almost nothing. A bit farther out, a few scattered galaxies. Farther still, more galaxies appearing more frequently. Eventually, you reach the filaments and sheets that surround the void, where galaxy density is higher than the cosmic average. This creates a hierarchical structure, small voids nested within larger voids, filaments and sheets separating voids of different sizes, the cosmic web at multiple scales simultaneously. Voids grow over time. As the universe expands and matter continues to flow from voids into filaments, the contrast between empty and full regions becomes more extreme. Voids that were only slightly underdense in the early universe have become severely underdense today. This growth has been ongoing for billions of years, but it's slowing now as dark energy dominates the expansion. In the past, when matter dominated, gravity was pulling matter out of voids rapidly. Now, with dark energy driving accelerated expansion, the evacuation has slowed. Voids are still growing, but more gradually. In the far future, as dark energy's influence continues to increase, voids will eventually stop growing altogether. The expansion will become so fast that even the weak forces pulling matter out of voids will be overwhelmed. The cosmic web will freeze in its final configuration, unable to evolve further. But that's billions of years away. For now, voids are still active participants in cosmic evolution, still evacuating matter, still growing, still shaping the large-scale structure of the universe. What would it be like to exist in a void? Imagine a civilization arising on a planet in a void galaxy. When they looked up at their night sky, they would see something very different from what we see. Their own galaxy would be visible, a band of stars stretching across the darkness, just as the Milky Way appears to us. But beyond their galaxy, they would see almost nothing. Where we see thousands of galaxies visible to small telescopes, they might see only a handful, faint smudges at the edge of detectability. Their cosmic horizon would feel much closer. They might conclude that their galaxy was alone, or nearly alone, in an infinite dark universe. It would take very sophisticated observations to detect the faint distant galaxies at the edges of the void, and even more sophisticated observations to realize that beyond those edges, the universe is filled with galaxies.